The universe is older than it should be, not by a little, not by a rounding error in some cosmologist's spreadsheet, by billions of years, and the proof is staring back at us from 13 billion light-years away, frozen in ancient light that left its source when our universe was 300 million years old. A newborn, an infant cosmos that should have been dark, empty, scattered with the first sparks of hydrogen attempting to collapse into something resembling a star. That was the plan. That was the timeline every model agreed on. The James Webb Space Telescope was built to see that moment, to catch the universe in its crib, to photograph the dim, chaotic beginnings of everything. What it found instead were galaxies. Not proto-galaxies, not half-formed clumps of gas struggling to ignite. Fully formed, massive, impossibly mature galaxies containing hundreds of billions of stars, galaxies that require 2 to 3 billion years of uninterrupted stellar evolution to build. Sitting there, waiting, in a universe that was 300 million years old. The math does not work, the physics does not allow it. The timeline makes no sense. And yet the images keep coming in, sharper and stranger with every observation. Scientists are not debating whether these galaxies are real. They are debating whether our entire understanding of cosmic history is wrong. Because if these objects exist where they exist, when they exist, with the mass and structure they clearly possess, then something about the birth of our universe has been fundamentally misunderstood. This is not a minor discrepancy. This is not a tweak to the model. This is the kind of discovery that erases textbooks, and it is happening right now. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Before the James Webb Space Telescope opened its golden mirror to the sky, we thought we had the story figured out. The universe began 13.8 billion years ago in a moment of incomprehensible violence and heat. Energy condensed into matter, matter cooled into atoms, atoms clustered into the first stars, stars assembled into galaxies, galaxies organized into clusters and superclusters, weaving themselves into the vast cosmic web we observe today. It was a beautiful story, clean, logical, supported by decades of observation and mathematical modeling. The lambda cold dark matter model, the standard framework of modern cosmology, described this progression with remarkable precision. It explained the distribution of galaxies across billions of light-years. It predicted the patterns we see in the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. It accounted for the expansion of space, the acceleration driven by dark energy, the gravitational scaffolding provided by dark matter. For nearly half a century, this model withstood challenge after challenge, growing more refined with each new telescope, each new survey, each new data set. And at the heart of that model was a timeline, a schedule for when things happened and in what order. The Big Bang was not an explosion in space, it was an explosion of space itself. In the first fraction of a second, the universe expanded from something smaller than an atom to something larger than a galaxy. The temperatures were so extreme that matter as we know it could not exist. Only after the universe had cooled for about 380,000 years did atoms finally stabilize enough to let light travel freely through space. That moment, when photons decoupled from matter and began their journey across the cosmos, left behind the cosmic microwave background, a snapshot of the infant universe frozen in radiation. We can still see it today, faint and cold, stretched by 13 billion years of expansion into the microwave portion of the spectrum. But after that moment, the universe went dark, completely, utterly dark. There were no stars yet. No galaxies, no light sources of any kind except the fading glow of the Big Bang itself, redshifting into invisibility. This era is called the Cosmic Dark Ages, and it lasted for tens of millions of years, maybe 100 million, maybe more. During that time, the universe was filled with neutral hydrogen and helium gas, the only two elements created in significant quantities during the Big Bang. That gas drifted through the darkness, clustering slowly under the influence of gravity into denser and denser pockets. The densest regions pulled in more gas. The more gas they accumulated, the stronger their gravitational pull became. Eventually, these pockets grew massive enough and dense enough that their cores ignited. Hydrogen atoms fused into helium, energy poured outward, the first stars lit up. Astronomers call them population 3 stars, and no human being has ever seen one. We have never detected one directly. They exist only in theory and in computer simulations, but the theory is solid. These stars were enormous, hundreds of times more massive than our Sun, burning ferociously hot and dying young. They had no heavy elements in their composition because no heavy elements existed yet. They were pure hydrogen and helium, the primordial ingredients, and they burned with a kind of reckless intensity that stars today cannot match. Within a few million years, they exhausted their fuel and exploded as supernovae, scattering the first heavy elements into the surrounding gas: carbon, oxygen, nitrogen, iron. The ashes of the first generation of stars became the raw material for the second generation. And from that second generation, enriched with heavier elements, the first true galaxies began to form. According to the lambda cold dark matter model, this process took time, a lot of time. The first stars were expected to appear somewhere between 100 and 200 million years after the Big Bang. The first small protogalaxies, clumpy, irregular collections of a few million stars held together by dark matter, were predicted to emerge around 300 to 500 million years after the Big Bang. These early galaxies would be small, chaotic, disordered. They would merge with one another over hundreds of millions of years, gradually building larger structures. The grand spiral galaxies and massive elliptical galaxies we see in the nearby universe today were expected to be the result of billions of years of slow hierarchical assembly. You do not build a skyscraper in a week. You pour the foundation, you erect the frame, you add floors one by one. The universe, according to our best models, followed a similar blueprint. Start small, build slowly, add complexity over time. That was the expectation when the James Webb Space Telescope launched on Christmas Day in 2021. The telescope itself had been in development for more than 2 decades, a collaboration involving thousands of engineers, scientists, and technicians across multiple countries. Its primary mirror spans 5 meters, composed of 18 hexagonal segments coated in a microscopically thin layer of gold to reflect infrared light with maximum efficiency. Unlike the Hubble Space Telescope, which orbits Earth, Webb sits at a gravitationally stable point called Lagrange 2, roughly 1.5 million kilometers from our planet. From that vantage, it is shielded from the heat and light of both the Earth and the Sun by a 5-layer sun shield the size of a tennis court. This allows its instruments to cool to temperatures just a few dozen degrees above absolute zero, sensitive enough to detect the faint infrared glow of the most distant objects in the universe. And distant means old. When we look at a galaxy a billion light-years away, we are not seeing it as it exists today. We are seeing it as it was a billion years ago, because the light from that galaxy has taken a billion years to reach us. The further away an object is, the further back in time we are looking. This is called look-back time, and it is one of the most powerful tools astronomy has. Telescopes are time machines. They let us observe the history of the universe directly, layer by layer, by simply pointing at increasingly distant objects. The most distant galaxies visible to Hubble were seen as they existed about 400 million years after the Big Bang, at a redshift of around 11. Redshift is the measure astronomers use to quantify distance and age in cosmology. As space expands, the light traveling through it gets stretched, shifting toward the red end of the spectrum. The more stretched the light, the further it has traveled, and the higher the redshift number. A redshift of 1 corresponds to a look-back time of about 8 billion years. A redshift of 6 takes you back to when the universe was less than 1 billion years old. A redshift of 10 or higher puts you in the era of the first galaxies, the cosmic dawn, the moment the lights came on. Webb was built to see past Hubble's limit. Its infrared sensitivity allows it to detect light that has been stretched beyond what Hubble's instruments could register. The goal was to find galaxies at redshifts of 15 or higher, galaxies forming just 200 or 250 million years after the Big Bang. Scientists expected these galaxies to be faint, small, and difficult to detect. They expected to see the universe in its awkward adolescence, still figuring out how to build structure, still experimenting with star formation. The predictions were cautious, conservative, grounded in decades of data. Within months of beginning observations, Webb shattered those predictions. It did not find small, faint protogalaxies struggling to hold themselves together. It found massive, mature galaxies shining brightly at redshifts higher than anything Hubble had ever confirmed. Galaxies at redshift 13, redshift 14, galaxies that existed just 300 million years after the Big Bang, a time when the universe was barely 2% of its current age. And these were not marginal detections. They were clear, unambiguous, sitting right there in the data, like facts that refused to behave. Understanding what that means requires understanding the numbers. When we say a galaxy is 5 billion light-years away, we are using a measure called look-back distance. That is how far the light has traveled to reach us. But because the universe has been expanding the entire time that light was in transit, the galaxy itself is now much farther away than 5 billion light-years. The actual distance today, accounting for expansion, is something closer to 8 billion light-years. This is called the proper distance or moving distance, and it reflects the current size of the observable universe. The observable universe has a radius of about 46 billion light-years in every direction, even though the universe is only 8 billion years old. That is not a contradiction, that is expansion. But the look-back distance is what matters for understanding what we are seeing. A galaxy 5 billion light-years away in look-back distance means we are seeing light that left that galaxy 5 billion years ago. If the universe is 8 billion years old, and we are looking at light from 5 billion years ago, then we are seeing that galaxy as it existed just 300 million years after the Big Bang. 300 million years sounds like a long time. It is not on cosmic scales. Earth itself is 5 billion years old. The Sun is 6 billion years old. The dinosaurs went extinct 66 million years ago. 300 million years after the Big Bang is the equivalent of looking at a newborn baby and expecting to find a fully formed adult. And the conditions at that time were nothing like the universe we know today. At 300 million years, the universe contained almost no heavy elements. When astronomers talk about heavy elements, they mean anything heavier than helium, carbon, oxygen, nitrogen, silicon, iron. All of these are produced inside stars through nuclear fusion, and all of them are scattered into space when stars die. But 300 million years after the Big Bang, the first generation of stars had only just begun to explode. The gas clouds from which new stars were forming were still more than 99% hydrogen and helium. There was no iron to form rocky planets. There was no oxygen to combine with hydrogen and create water. There was no carbon to build organic molecules. The universe at that moment was chemically barren, a vast ocean of the two lightest elements, barely beginning to be seasoned with traces of anything else. In that environment, stars formed differently than they do today. Without heavy elements to help cool the gas, the clouds that collapsed to form stars had to be hotter and more massive. This made the stars themselves larger, hotter, and shorter-lived. They burned through their fuel quickly and died in violent explosions, enriching the surrounding gas little by little. The process of building a galaxy required multiple generations of stars, each one contributing a bit more chemical diversity, each one dying and recycling its material back into the cosmic mix. This takes time, lots of time, hundreds of millions of years according to every model we had. The expectation was that galaxies observed at 300 million years after the Big Bang would be small, perhaps a few 100 million times the mass of our Sun, composed of young, hot stars with almost no heavy elements in their spectra. They would be irregular in shape, lacking the organized structure of spiral arms or elliptical symmetry. They would be faint, sitting right at the edge of Webb's detection capability. The universe at that age was supposed to be a rough draft, not a finished manuscript. Webb was designed to read that rough draft. Its near-infrared camera, called NIRCam, can capture images across a range of infrared wavelengths, detecting the stretched light from galaxies at redshifts well beyond 10. Its near-infrared spectrograph, NIR-SPEC, can split that light into its component wavelengths, revealing the chemical fingerprints of the stars and gas inside those galaxies. Together, these instruments allow astronomers to measure not just how far away a galaxy is, but what it is made of, how fast it is forming stars, and how much mass it has accumulated. The first deep-field images from Webb were released in July 2022, less than 7 months after launch. The images were stunning. Thousands of galaxies scattered across a patch of sky no larger than a grain of sand held at arm's length. Galaxies of every shape and color, some nearby and familiar, others distant and strange. Among them were galaxies that appeared as faint red smudges, their light stretched so dramatically by the expansion of space that they glowed only in the deepest infrared wavelengths. These were the targets. These were the objects astronomers had been waiting decades to see. Follow-up observations confirmed what the images suggested. Several of these galaxies sat at redshifts above 13. One, catalogued as JWST 13-0, clocked in at a redshift of 13. 2. Another, JWST 14-0, pushed even higher to a redshift around 14. 3. Both were detected as part of the JWST Advanced Deep Extragalactic Survey, or JADES, a coordinated observing program designed to find and characterize the most distant galaxies in the universe. The redshifts placed these galaxies at look-back times of 13.4 to 13.5 billion years. They were being seen as they existed 280 to 290 million years after the Big Bang. That alone would have been remarkable. Finding galaxies that early was exactly what Webb was built to do. But the remarkable part was not that they were found. The remarkable part was what they looked like when the data came in. These were not the small, irregular clumps of stars the models predicted. These were galaxies with masses measured in the hundreds of millions to low billions of solar masses. Galaxies bright enough to be detected clearly and analyzed in detail. Galaxies that, by every rule we thought we understood, should not have had time to form yet. And it was not just their size, it was their chemistry. When astronomers analyzed the spectra of these galaxies, they found emission lines corresponding to oxygen. Oxygen is a heavy element produced only inside massive stars and released into space when those stars explode as supernovae. Detecting oxygen in a galaxy 290 million years after the Big Bang means that stars had already formed, lived their entire lives, died, and enriched the surrounding gas with the products of their fusion. All of that had to happen within the first couple hundred million years of cosmic history. The timeline was tight, uncomfortably tight. The universe we thought we understood had rules, it had a pace, it had a schedule. The James Webb Space Telescope pointed its mirror at the earliest moments of that schedule and found something that did not fit. Not a small deviation, not a minor discrepancy that could be explained away with a tweak to the models. Something fundamentally inconsistent with the story we had been telling for half a century. Before Webb, we believed the cosmic dawn was a slow and gradual process. After Webb, we are no longer sure what to believe. The data is clear, the galaxies are there, the chemistry is real, the timeline does not work, and if the timeline does not work, then something else in the model has to give. Either our understanding of how stars form is wrong, or our understanding of how galaxies assemble is wrong, or our understanding of the early universe itself is wrong. The foundation we thought was solid has cracks running through it, and those cracks are only getting wider. The first hint that something was wrong came on July 11, 2022, less than 7 months after Webb launched. NASA released the telescope's first deep field image to the public, a photograph of a galaxy cluster called SMACS 723 that had been exposed for more than 12 hours. The image was breathtaking. Thousands of galaxies scattered across the frame, some bright and nearby, others faint and stretched into arcs by the gravitational lensing effect of the massive cluster in the foreground. News outlets called it the deepest image of the universe ever taken. Scientists called it something else. They called it confusing. Among the thousands of galaxies in that image were a handful of faint red smudges, barely visible against the black background. These were not foreground objects. They were galaxies sitting at the very edge of the observable universe, their light stretched so dramatically by cosmic expansion that it had shifted entirely out of the visible spectrum and deep into the infrared. Webb's instruments were designed to see exactly this kind of light. What they were not designed for was what came next. Within days, the first analyses started appearing on preprint servers. Astronomers were using Webb's spectroscopic data to measure the redshifts of these distant galaxies, and the numbers were higher than anyone had expected. Redshift 10, redshift 11, then redshift 12, then 13. Each new detection pushed further back in time, closer to the Big Bang, into an era that was supposed to be dim and underdeveloped. The galaxies were there, clearly visible, glowing brightly enough to be studied in detail, and they should not have been. One of the first major announcements came from the GLASS survey, short for GRISM Lens Amplified Survey from Space. The team, led by Tommaso Tro at UCLA, had pointed Webb at a cluster called Abell 2744, using the cluster's gravity to magnify the light from background galaxies. Among the objects they found was a galaxy they catalogued as GLASS ZAAA13, sitting at a redshift of 13.2. The light from this galaxy had been traveling for more than 13.4 billion years, It was being observed as it existed just 300 million years after the Big Bang. That alone would have been a milestone. Hubble had never confirmed a galaxy beyond a redshift of about 11, and even those detections were marginal, sitting right at the edge of the telescope's capabilities. Glass Z13 was clear. The spectrum was clean. The redshift was unambiguous. But the real surprise was not the distance. It was the mass. When astronomers measured the brightness of the galaxy and compared it to the distance, they calculated that it contained roughly 100 million times the mass of our Sun in stars, 100 million solar masses. For a galaxy that had only 300 million years to form, that number was uncomfortable. Stars do not assemble instantly. They take time to collapse out of gas clouds, time to ignite, time to burn through their fuel. In the early universe, where the gas was almost entirely hydrogen and helium with no heavy elements to help it cool, star formation should have been slower, not faster. The models predicted that galaxies at this distance would be small and faint, clumpy collections of a few tens of millions of solar masses at most, still in the process of pulling themselves together. Glass Z13 looked more like a finished product than a prototype. Then came CEERS 1019, the Cosmic Evolution Early Release Science Survey, led by Stephen Finkelstein at the University of Texas, was one of the first major observing programs to run on Webb. The survey targeted a patch of sky called the Extended Growth Strip, a region that had been studied extensively by Hubble and other telescopes over the years. Finkelstein's team wanted to see what Webb could find in the same area, pushing deeper into the infrared and further back in time. What they found was a galaxy that broke the script completely. CEERS 1019 sits at a redshift of 9.1. That places it about 500 million years after the Big Bang, later than Glass Z13, but still firmly in the era astronomers call the Cosmic Dawn. The shock was not the distance, it was the size. When the team analyzed the galaxy's light, they calculated a stellar mass of roughly 9 billion solar masses. 9 billion. That is not a small, irregular proto-galaxy struggling to hold itself together. That is a structure comparable in mass to the modern Milky Way, sitting in an era when the universe had not yet celebrated its first billion-year anniversary. To put that in perspective, our own galaxy is about 13 billion years old. It has spent the entire history of the universe growing, merging with smaller galaxies, accreting gas, forming new stars. The Milky Way today contains somewhere between 200 and 400 billion stars, with a total stellar mass estimated at around 50 to 60 billion solar masses. CEERS 1019, at just 500 million years old, already had roughly 1/6 of that. It was not a baby, it was a teenager pretending to be an adult, and the universe had barely given it time to get dressed. The discovery of CEERS 1019 sent ripples through the community. Papers were written, conferences were held, and the word crisis started appearing in headlines. Some astronomers pushed back, arguing that the mass estimates might be inflated. Galaxies this distant are faint, and measuring their brightness accurately is difficult. Small errors in the measurement can lead to large errors in the calculated mass. Others pointed out that some of the light might not be coming from stars at all. It could be coming from an active supermassive black hole at the galaxy's center, a quasar-like object whose intense radiation could mimic the signature of a much larger stellar population. If that were the case, the actual stellar mass might be lower, and the tension with the models would ease. Finkelstein's team anticipated that argument. They ran follow-up observations using Webb's near-infrared spectrograph, an instrument that does not just take pictures but splits incoming light into its component wavelengths. By examining the spectrum in detail, they could distinguish between light from stars and light from an active black hole. The two have different fingerprints. Stars emit a broad, continuous spectrum with absorption lines, where cooler gas in the star's outer layers blocks specific wavelengths. Active black holes, by contrast, produce emission lines, bright spikes at specific wavelengths caused by superheated gas spiraling into the black hole's accretion disk. The spectrum of CRS 1019 showed both. There was a black hole at the center, and it was active, but it was not responsible for all the light. Most of the galaxy's luminosity came from stars, lots of stars. The mass estimate held. The galaxy was genuinely massive, and it was genuinely there, shining brightly in an era when it had no business being so well developed. Then in early 2024, another team announced the discovery of JWST 14-0, and the timeline got even tighter. JWST stands for the JWST Advanced Deep Extragalactic Survey, a collaboration involving dozens of institutions and hundreds of hours of telescope time. The survey was designed to push Webb to its absolute limits, hunting for galaxies at redshifts higher than anyone had confirmed before. JWST 14-0 came in at a redshift of 14.3, placing it at a look-back time of 13.5 billion years. The galaxy was being seen as it existed just 290 million years after the Big Bang. At first, some astronomers thought the detection might be a fluke. Redshift measurements at these extreme distances are tricky. The light is faint, the signal is weak, and contamination from foreground sources can mimic the signature of a high redshift galaxy. The JWST team ran multiple checks. They observed the galaxy with different instruments, analyzed the spectrum from multiple angles, and cross-referenced the data with independent observations. Every test confirmed the result. The galaxy was real, it was distant, and it was glowing with the light of roughly 100 million solar masses worth of stars. What made JWST 14-0 even stranger was its chemistry. When the team examined the galaxy's spectrum, they found strong emission lines corresponding to doubly ionized oxygen, a signature that only appears when massive stars have already lived and died in large numbers. Oxygen is not a primordial element. It does not exist in the hydrogen and helium fog left over from the Big Bang. It has to be forged inside stars through nuclear fusion, built up atom by atom in the cores of massive suns, and then scattered into space when those stars explode as supernovae. Detecting oxygen in a galaxy 290 million years after the Big Bang means that at least one full generation of stars had already formed, burned through their fuel, and died, all within a window of time that should not have been long enough for any of that to happen. The timeline does not add up. Population 3 stars, the first generation, are expected to take tens of millions of years to form after the Big Bang. They live fast, maybe a few million years at most, and then they explode. The gas from their explosions has to cool, collapse, and form the next generation of stars. Those stars have to build up enough heavy elements to alter the chemistry of their surroundings. Then, those stars have to die and enrich the gas further. Only after multiple cycles of this process do you start to see significant amounts of oxygen in a galaxy's spectrum. The standard models suggested this would take at least 500 million years, maybe longer. JWST 14-0 did it in less than 300. For context, 300 million years is not a lot of time on cosmic scales. The dinosaurs walked the Earth for about 165 million years. Humans have existed for roughly 300,000 years. The gap between the Big Bang and JWST 14-0 is shorter than the gap between the formation of Earth and the present day. And yet, in that narrow slice of time, this galaxy managed to form stars, evolve chemically, build up a mass of 100 million suns, and develop a structured enough environment to hold itself together against the chaotic conditions of the early universe. It is like planting a seed and coming back an hour later to find a forest. The question everyone started asking was how? How does a galaxy form that fast? How does it accumulate that much mass in such a short time? How does it enrich itself with heavy elements when there has barely been time for the first stars to die? The lambda cold dark matter model, the standard framework of cosmology, does not have good answers to these questions. The model works by assuming that structure forms hierarchically. Small things first, then bigger things, then even bigger things. Dark matter clumps together under gravity, forming halos. Gas falls into those halos and cools. Stars form. Galaxies build up slowly over hundreds of millions of years through a combination of star formation and mergers with smaller neighbors. It is a bottom-up process, gradual and patient. But the galaxies Webb was finding did not look gradual. They looked like they had skipped steps. One possibility is that star formation in the early universe was far more efficient than anyone expected. In the modern universe, only about 10% of the gas in a galaxy actually turns into stars. The rest is either too hot, blown away by stellar winds and supernova explosions, or simply too diffuse to collapse. But in the early universe, conditions were different. The gas was denser. There were no heavy elements to produce dust, and dust is one of the main things that regulates star formation by absorbing and re-radiating energy. Without dust, gas clouds could collapse faster and more completely. If star formation efficiency in the first few 100 million years was not 10% but 50% or even higher, galaxies could build mass much more quickly. Some simulations support this idea. Researchers have run models of the early universe where they cranked up the star formation efficiency to see what would happen. The results show that under the right conditions you can form galaxies with masses in the hundreds of millions of solar masses by 300 million years after the Big Bang. The models work, but only if you push the parameters to their limits. And even then, the galaxies you get are right at the edge of what is physically plausible. They are not impossible, but they are uncomfortably close. Another possibility is that these early galaxies were fed by unusually large streams of gas funneled directly into their cores by the cosmic web. In the first few 100 million years after the Big Bang, the universe was still a tangled mess of filaments and voids, with rivers of gas flowing along the densest structures. If a galaxy happened to sit at the intersection of multiple filaments, it could receive a steady supply of fresh gas, fueling rapid star formation. Some astronomers call these cold streams, and they show up in simulations as narrow channels of cool, dense gas threading through the hot, diffuse medium of the early universe. If JWST 14-0 and galaxies like it were sitting at the mouths of these streams, they would have had access to far more raw material than a typical galaxy, giving them a massive head start. The third possibility is the one that makes everyone nervous. Maybe some of the light we are seeing is not coming from stars at all. Maybe it is coming from supermassive black holes. Quasars, the brightest objects in the universe, are powered by black holes weighing millions or even billions of times the mass of the Sun. Gas spiraling into these black holes heats up to millions of degrees, emitting radiation across the entire electromagnetic spectrum. A single quasar can outshine an entire galaxy of stars. If the galaxies Webb is detecting have active supermassive black holes at their centers, the light from those black holes could be inflating the apparent stellar mass, making the galaxies look more massive than they actually are. There is evidence that some of these early galaxies do harbor supermassive black holes. CER's 1019, for example, has a confirmed active nucleus. The spectrum shows emission lines characteristic of gas being heated by a black hole. But even after accounting for the black hole's contribution, the galaxy still appears to have billions of solar masses in stars. The black hole is part of the story, but it is not the whole story. And that raises another uncomfortable question. How do you grow a supermassive black hole in the first few 100 million years after the Big Bang? Black holes grow by eating matter. The more they eat, the bigger they get. But there is a limit to how fast they can grow, set by the radiation pressure of the infalling material. Feed a black hole too fast, and the radiation pushes away the gas before it can fall in. This limit, called the Eddington limit, means that even under ideal conditions, a black hole can only double its mass every few tens of millions of years. Start with a stellar mass black hole, maybe 10 times the mass of the Sun, and grow it at the Eddington limit for 300 million years, and you end up with a black hole weighing a few million solar masses at most. Some of the black holes detected in these early galaxies are already in that range. They are sitting right at the edge of what the growth models allow, and they got there impossibly fast. One way around this is to start with a much bigger seed. Instead of forming from the collapse of a single massive star, what if some black holes formed directly from the collapse of entire gas clouds in the early universe? These so-called direct collapse black holes could start out weighing tens or even hundreds of thousands of solar masses, giving them a huge head start. Grow a black hole like that at the Eddington limit, and you can reach millions or billions of solar masses within a few 100 million years. The math works, but nobody has ever observed a direct collapse black hole forming. It is a theoretical solution to a theoretical problem, and the evidence is circumstantial at best. The debate over these early massive galaxies is not just about numbers. It is about whether the framework we have been using to understand the universe is robust enough to handle what we are seeing. The lambda cold dark matter model is extraordinarily successful. It explains the large-scale structure of the universe, the distribution of galaxies, the patterns in the cosmic microwave background, the acceleration of cosmic expansion. It has passed every major test thrown at it for the better part of half a century, but it was built on observations of the nearby universe, the universe as it exists today and as it existed a few billion years ago. The early universe, the first few 100 million years, has always been harder to observe. Hubble could barely touch it. Webb is the first telescope with the sensitivity to see that era clearly, and what it is seeing does not quite match the predictions. Stephen Finkelstein, the lead astronomer on the CEERS survey, put it plainly in an interview with Nature in 2024. He said that the model cosmologists were using when Webb launched is not the model they are using now. That is not an admission of failure. That is how science works. You build a model based on the data you have. You make predictions, you test those predictions with new observations. If the observations do not match, you revise the model. The question is how much revision is needed. Are we talking about a minor adjustment, a tweak to a few parameters, or are we talking about something deeper, a fundamental rethinking of how galaxies form in the early universe? For now, the answer is somewhere in the middle. The lambda cold dark matter model is not broken, but it is being stretched. The galaxies Webb is finding are not impossible, but they are improbable. They sit right at the edge of what the models allow, and there are more of them than anyone expected. By 2025, Webb had identified roughly 300 candidate massive galaxies at redshifts above 10. 300. The original predictions suggested there should be a few dozen at most. Even after correcting for contamination from foreground sources and accounting for active black holes, the number of massive early galaxies is still 2 to 10 times higher than the models predicted. That is not a rounding error. That is a systematic discrepancy, and it demands an explanation. The detection method itself is worth understanding because it is what makes all of this possible. Webb does not see galaxies the way our eyes see objects. It sees them as patterns of infrared light, photons that have been traveling through space for more than 13 billion years, stretched by expansion into wavelengths far beyond what the human eye can perceive. The telescope's near-infrared camera, NIR-CAM, captures images across a range of wavelengths from about 0.6 to 5 microns. For comparison, visible light ranges from about 0.4 to 0.7 microns. Everything Webb sees is redder than red, deeper into the infrared than Hubble could ever reach. When NIR-CAM takes a picture, it does not just record a single image. It records multiple images at different wavelengths, building up a color map of the sky. Nearby galaxies appear bright across many wavelengths. Distant galaxies, their light stretched by redshift, appear faint and only show up in the reddest filters. By comparing the brightness of a galaxy across different filters, astronomers can estimate its redshift. This is called photometric redshift, and it is a quick way to identify distant candidates, but it is not precise. Photometric redshifts can be off by 10 or 20%, and in some cases they can be fooled entirely by foreground objects whose light happens to mimic the signature of a high redshift galaxy. To confirm a detection, astronomers use spectroscopy. Webb's near-infrared spectrograph, NIR-SPEC, splits the light from a galaxy into its component wavelengths, producing a spectrum. The spectrum reveals absorption and emission lines, dark and bright features at specific wavelengths corresponding to different chemical elements. Hydrogen, helium, oxygen, carbon, each one leaves a unique fingerprint. In a distant galaxy, those fingerprints are shifted toward the red end of the spectrum by a precise amount determined by the redshift. Measure the shift, and you have the distance. Measure the intensity of the lines, and you have the chemistry. Measure the overall brightness, and you have the mass. This is how GLASS Z13, Sears 1019, and JAYS GSZ140 were confirmed. Photometric observations flagged them as distant candidates. Spectroscopic follow-up locked in their redshifts and revealed their properties. The process is painstaking. Each spectrum requires hours of telescope time. Each galaxy has to be carefully selected, observed, and analyzed. But the results are unambiguous. These galaxies are real, they are distant, they are massive, and they are forcing astronomers to ask whether the universe we thought we understood is the universe that actually exists. Hubble, for all its achievements, could not have done this. Hubble's farthest confirmed galaxy, GNZ11, sits at a redshift of about 11.1. It was discovered in 2016 after years of deep observations and careful analysis. The galaxy appeared as a faint red smudge in Hubble's images, sitting right at the edge of the telescope's sensitivity. Its mass was estimated at around 1 billion solar masses. Large for its time, but not shockingly so. Hubble's instruments were limited by their wavelength range. They could detect light out to about 1.6 microns in the infrared, but beyond that they were blind. Galaxies at redshifts above 11 emit most of their light at wavelengths longer than Hubble could see. They were there, glowing in the dark, but Hubble could not find them. Webb changed that. Its sensitivity extends out to 5 microns and beyond, deep into the mid-infrared. The galaxies that were invisible to Hubble are bright and clear to Webb, and there are a lot of them, far more than the models predicted. The universe, it turns out, was busier in its infancy than anyone realized. Stars were forming faster. Galaxies were assembling more efficiently. The cosmic dawn was not a slow, gradual brightening. It was a sudden ignition, a moment when the universe went from dark to blazing in what amounts to the blink of an eye on cosmic timescales. The implications are still being worked out, papers are being written, models are being revised, conferences are being held where scientists debate the finer points of star formation efficiency and black hole growth rates and the role of dark matter in the early universe. The consensus is shifting slowly toward the idea that the lambda cold dark matter model is still fundamentally correct but needs adjustments. Higher star formation efficiency, more efficient gas accretion, perhaps a different initial mass function, the distribution of stellar masses that determines how many large stars versus small stars form in a given burst of star formation. These are not small changes, but they are changes that fit within the existing framework. The model bends, it does not break, but the cracks are there, and the more Webb looks, the wider those cracks seem to grow. The problem is not that these galaxies are far away. Distance in astronomy is just a technical challenge. Build a bigger mirror, cool it down to near absolute zero, park it 1.5 million kilometers from Earth, and you can see further. The James Webb Space Telescope did exactly that, and it worked. The problem is not the seeing, the problem is the when. When we look at a galaxy 13 billion light-years away, we are seeing it as it existed 13 billion years ago. The light we are detecting tonight left that galaxy when the universe was less than 1 billion years old. We are not observing the present. We are observing the past, directly, in exquisite detail. And the past we are seeing does not match the past we expected. The galaxies Webb found in the first few 100 million years after the Big Bang are not small and primitive. They are large and developed. They contain hundreds of millions to billions of solar masses worth of stars. They show evidence of chemical enrichment, the presence of oxygen and carbon and other heavy elements that can only be produced inside stars over multiple generations. And all of that, according to every model of stellar evolution we have, should have taken far longer than the time available. This is the time paradox, not a paradox in the sense of a logical contradiction, but a paradox in the sense of something that should not fit but does. The universe at 300 million years old was an infant. The galaxies we are seeing in that infant universe look like teenagers, and the gap between infant and teenager is not being explained by any process we currently understand. To see why this is such a problem, you need to understand how galaxies are supposed to grow, not in theory but in practice, the mechanics. The step-by-step process that turns a cloud of primordial gas into a shining collection of billions of stars. Because that process, as far as we know, cannot be rushed. It has speed limits built into the physics, and those speed limits are being violated. Start with the raw material. After the Big Bang, the universe was filled with hydrogen and helium. Roughly 75% hydrogen by mass, 25% helium, and trace amounts of lithium. That is it. No carbon, no oxygen, no nitrogen, no iron, no silicon, nothing heavier than the third element on the periodic table. These three elements, hydrogen, helium, and lithium, are the only ones produced in significant quantities during the first few minutes of the universe's existence, in the brief window when temperatures and densities were high enough for nuclear fusion to occur throughout all of space. Once the universe cooled below the threshold for fusion, element production stopped. For the next few 100 million years, the chemical composition of the universe did not change. It was a universe of 3 ingredients, and every structure that would eventually form, every star, every planet, every atom in your body, had to be built starting from just those 3. The first stars began to form when the universe was somewhere between 100 and 200 million years old. These stars, called population 3 stars, were nothing like the Sun. They were enormous. possibly hundreds of times more massive, burning at ferocious temperatures. The reason they were so large has to do with cooling. When a cloud of gas collapses under its own gravity, it heats up. The more it collapses, the hotter it gets. Eventually, if the core gets hot enough, hydrogen fusion ignites and a star is born. But for the collapse to continue in the first place, the gas has to be able to radiate away some of that heat. If it cannot cool, the pressure from the heat will stop the collapse before a star can form. In the modern universe, gas clouds cool efficiently because they contain trace amounts of heavy elements. Carbon, oxygen, and other molecules act as coolants, absorbing thermal energy and re-radiating it as infrared light. This allows the gas to collapse into relatively small, dense clumps, forming stars with masses similar to our Sun or smaller. But in the early universe, there were no heavy elements. The gas could only cool through molecular hydrogen, a much less efficient process. As a result, the clouds that collapsed had to be much larger and much hotter before they could form stars. The stars that resulted were massive, blue, and short-lived. These first stars burned through their fuel in just a few million years. When they exhausted the hydrogen in their cores, they began fusing helium into carbon, carbon into oxygen, oxygen into neon, and so on up the periodic table until their cores were filled with iron. Iron is the end of the line. Fusing iron does not release energy, it absorbs energy. When a massive star's core turns to iron, fusion stops. The core collapses in less than a second. The outer layers rebound off the collapsing core and explode outward in a supernova, one of the most violent events in the universe. In that explosion, the star's outer layers, now enriched with all the elements it had been fusing for millions of years, are scattered into space. Carbon, oxygen, nitrogen, silicon, iron, all of it seeded into the surrounding gas clouds. This is how the universe gets its heavy elements. Stars are factories. They take hydrogen and helium, the raw materials, and through fusion, they build everything else. When they die, they distribute the products. The next generation of stars forms from gas that is slightly enriched with these heavier elements. Those stars, in turn, produce more heavy elements and scatter them when they die. Generation after generation, the chemical composition of the universe becomes more complex. Astronomers call this metallicity, the fraction of a star's or galaxy's composition that is made up of elements heavier than helium. Higher metallicity means more generations of stars have lived and died in that region. The process takes time, a lot of time. The first generation of stars, population 3, had zero metallicity, pure hydrogen and helium. They lived for a few million years, then exploded. The gas from their explosions had to cool and collapse again to form the second generation, population 2 stars. These stars had low metallicity, just a tiny fraction of a percent of heavy elements, but it was enough to change how they formed. They could be smaller than population 3 stars, though still larger and hotter than the Sun. Population 2 stars lived longer, tens to hundreds of millions of years depending on their mass, and when they died, they enriched the gas further. The third generation, population 1 stars, which includes our Sun, formed from gas with even higher metallicity, roughly 2% heavy elements by mass. This allowed stars like the Sun to form, mid-sized, stable, long-lived. Each generation requires the previous generation to live and die first. You cannot skip steps. You cannot have a high metallicity star without first having low metallicity stars to produce the heavy elements. And you cannot have a galaxy full of stars at different stages of evolution without giving the process enough time to cycle through multiple generations. This is the bottleneck, the metallicity bottleneck. It is a hard limit on how fast a galaxy can chemically mature. The standard models, built on decades of observation and simulation, predicted that this process would take at least 500 million to a billion years to produce galaxies with significant metallicity. By 300 million years after the Big Bang, the universe should still be in the early stages of the first or second generation of star formation. The galaxies at that time should be small, chemically primitive, and composed almost entirely of massive, short-lived stars. They should have low metallicity, minimal structure, and masses in the tens to hundreds of millions of solar masses at most. That is not what Webb found. The galaxies detected at redshifts of 13 and 14, seen as they existed between 290 and 400 million years after the Big Bang, show clear evidence of oxygen in their spectra. Oxygen is not a first-generation element. It is produced in the cores of massive stars and ejected during supernova explosions. Detecting oxygen means that at least one, probably multiple generations of stars had already formed, lived and died by the time these galaxies were just a few 100 million years old. The metallicity bottleneck, the slow, patient process of building up heavy elements generation by generation, had somehow been bypassed, or compressed, or accelerated by a mechanism no one has yet identified. Consider the timeline in detail. The Big Bang happens at time zero. For the first 380,000 years, the universe is too hot for atoms to hold together. Photons scatter off free electrons in a dense fog. Then the universe cools enough for hydrogen atoms to form. The fog clears. The cosmic microwave background is released. For the next 100 to 200 million years, the universe is dark. No stars, just hydrogen and helium drifting through space, slowly clumping together under gravity. Then, at around 150 to 200 million years, the first stars ignite. These stars live for maybe 5 million years. Let us be generous and say 10 million years. Then they explode. Their debris has to disperse, cool, and collapse again. That takes another 10 to 20 million years. Now we are at 220 to 240 million years after the Big Bang, and we are just starting the second generation of star formation. The second-generation stars also have to live, evolve, and die before they can enrich the gas further. Depending on their masses, this takes anywhere from 10 million to a few 100 million years. Massive stars die quickly. Low-mass stars live a long time. For a galaxy to accumulate significant amounts of oxygen, you need a lot of massive stars to explode. That means a lot of star formation happening quickly. Fast enough to produce a large population of massive stars and then waiting for them to die. Even in the most optimistic scenario, where everything happens as fast as physics allows, you are looking at a minimum of 300 to 400 million years to go from the Big Bang to a galaxy with detectable oxygen lines in its spectrum. JWST 14-0, the galaxy at redshift 14.3, is being observed at 290 million years after the Big Bang. The oxygen is already there. The stars have already formed, lived, and died. The process happened faster than the minimum timeline allows, not slightly faster, significantly faster. Fast enough that it cannot be explained by simply tweaking the parameters of the existing models. Something fundamental is missing from our understanding of how star formation works in the early universe. One possibility is that the first generation of stars formed earlier than we thought. If population 3 stars ignited at 100 million years instead of 200 million years, that buys you an extra 100 million years for the chemical enrichment process. Some simulations suggest this is plausible. The densest regions of the early universe, the places where dark matter had already clumped together into the first halos, could have pulled in gas and triggered star formation as early as 50 to 100 million years after the Big Bang. If that happened, the timeline opens up slightly, not enough to make the problem go away, but enough to make it less severe. Another possibility is that star formation in the early universe was far more efficient than it is today. In the modern universe, only about 10% of the gas in a galaxy actually turns into stars. The rest either stays as gas, gets blown out by supernova explosions and stellar winds, or simply never collapses. But in the early universe, without heavy elements to regulate cooling, and without the feedback mechanisms that modern galaxies have developed over billions of years, star formation might have been much more efficient. Some models suggest efficiency rates as high as 50% or more. If half the gas in an early galaxy turned into stars instead of just 10%, you could build up a massive stellar population much faster. The problem with this idea is that it creates other problems. High-efficiency star formation means a lot of massive stars forming at once. Massive stars are hot and bright. They emit intense ultraviolet radiation that ionizes the surrounding gas and heats it up. This feedback can actually shut down star formation by preventing the gas from cooling and collapsing. The more efficient your star formation, the stronger the feedback, and the harder it becomes to keep the process going. There is a balance, and pushing star formation efficiency too high risks tipping the balance in the wrong direction. Some simulations show that you can get away with higher efficiency for a brief period, maybe a few tens of millions of years, before feedback takes over and star formation slows down. But even with that boost, reaching the masses and metallicities observed in the Webb galaxies is a stretch. A third possibility involves the initial mass function, the distribution of stellar masses that form in a given burst of star formation. In the modern universe, for every massive star that forms, dozens or hundreds of smaller stars form as well. The initial mass function is heavily weighted toward low-mass stars. But in the early universe, with no heavy elements and inefficient cooling, the initial mass function might have been different. It might have been top-heavy, producing a higher fraction of massive stars relative to low-mass stars. Massive stars die quickly and produce heavy elements. If the early universe was cranking out massive stars at a higher rate than we see today, the chemical enrichment process would happen faster. This is not a radical idea. Theoretical work going back decades has suggested that the first generation of stars should have a top-heavy initial mass function. The debate is over how top-heavy it was and how long that lasted. Some models predict that by the time the second generation of stars started forming, the initial mass function had already shifted to something closer to what we see today. Other models suggest it stayed top-heavy for longer, possibly for the first few 100 million years. If the latter is true, it could explain the rapid buildup of heavy elements in the early galaxies Webb is detecting. But it also means every simulation and model that assumed a modern initial mass function for the early universe is wrong and needs to be redone from scratch. Then there is the question of mass, not just chemical composition, but total stellar mass. How do you get a galaxy with hundreds of millions or even billions of solar masses worth of stars in just 300 to 500 million years? Stars form from gas. The gas has to fall into a dark matter halo, cool, collapse, and ignite. The rate at which this happens is limited by how fast gas can cool and how much gas is available. Dark matter halos grow over time by merging with other halos and by pulling in gas from their surroundings. The bigger the halo, the more gas it can hold and the more stars it can form. But halos do not grow instantly. They build up over hundreds of millions of years through a combination of smooth accretion and mergers. The lambda-cold dark matter model describes this process in detail. Dark matter, which does not interact with light or normal matter except through gravity, clumps together first. It forms the skeleton of cosmic structure, a web of filaments and nodes stretching across billions of light years. Normal matter, hydrogen and helium gas, falls into the gravitational wells created by the dark matter. The deepest wells, the most massive halos, pull in the most gas. Over time, these halos grow larger and more massive. Stars form in the centers of the halos where the gas is densest. Galaxies emerge as collections of stars held together by the gravity of the dark matter halo. This process is hierarchical. Small halos form first. They merge to create larger halos. Those larger halos merge to create even larger halos. At each step, more gas is pulled in, more stars form, and the galaxy grows. The timeline for this process is set by the rate at which dark matter halos collapse and merge, and that rate is determined by the density and distribution of matter in the early universe. According to the lambda cold dark matter model, the first small halos should appear around 100 to 200 million years after the Big Bang. These halos would have masses of around 1 million to 10 million times the mass of the Sun in dark matter. With a smaller amount of gas, the first stars would form in these halos. Over the next few 100 million years, these small halos would merge and grow. By 500 million years after the Big Bang, the largest halos would have masses of around 100 million to 1 billion solar masses in dark matter, with perhaps 10 to 100 million solar masses in stars, assuming 10% star formation efficiency. By 1 billion years, you could have halos massive enough to host galaxies like the Milky Way, though those galaxies would still be young and not as massive as the Milky Way is today. This is the timeline the models predict. The galaxies Webb is finding do not fit that timeline. CERS 1019, at a redshift of 9.1, sits at 500 million years after the Big Bang. The stellar mass is estimated at 9 billion solar masses. 9 billion. That is not a small irregular protogalaxy. That is a structure comparable in mass to the modern Milky Way. The dark matter halo needed to hold that much mass would have to weigh at least 10 times that, probably more. We are talking about a halo with a total mass of 100 billion solar masses or more, sitting in an era when the largest halos should be 1/10 of that size. For comparison, our Milky Way sits inside a dark matter halo with a total mass of around 1 trillion to 2 trillion solar masses. It took 13 billion years to build that halo. CERS 1019 seems to have built something comparable in just 500 million years. The math does not work. Halos grow by merging. Each merger roughly doubles the mass. Start with 1 million solar mass halo at 200 million years. Merge it with another halo of similar size at 300 million years. You now have a 2 million solar mass halo. Merge again at 400 million years, 4 million. Merge again at 500 million years, 8 million. Even if you assume a merger every 100 million years, which is faster than the models predict, you only get to a few tens of millions of solar masses by 500 million years. To reach 100 billion solar masses, you would need something like 12 or 13 doublings, 12 mergers in 300 million years. That is a merger every 25 million years. The models say that is not possible. Halos do not grow that fast, unless the halos started out much larger. If the initial seeds of dark matter halos were not 1 million solar masses but 10 million or 100 million, you get a massive head start. 100 million solar mass halo, growing through mergers every 50 million years, could reach 100 billion solar masses in 5 or 6 mergers. That takes 300 million years. The timeline barely fits. But this requires the initial conditions of the universe, the density fluctuations that seeded the formation of structure, to be much larger than what we observe in the cosmic microwave background. The cosmic microwave background shows the distribution of matter when the universe was 380,000 years old. The density fluctuations at that time were tiny, less than 1 part in 100,000. Those tiny fluctuations are what eventually grew into galaxies, but they grew slowly, over hundreds of millions of years, not tens of millions. If the initial fluctuations were larger, structure would form faster. But larger fluctuations would also show up in the cosmic microwave background, and they do not. The cosmic microwave background is remarkably smooth, almost perfectly uniform. The fluctuations we see are exactly the size needed to produce the universe we observe today, assuming the standard growth rate for structure formation. If you want structure to form faster, you need either larger initial fluctuations, which we do not see, or a different mechanism for accelerating growth, and no one has proposed a mechanism that works without breaking something else. There is also the issue of baryonic matter, the normal matter made of protons and neutrons that makes up stars and gas. Dark matter halos can grow by merging, but the gas inside those halos has to cool and fall to the center before it can form stars. That cooling process is not instantaneous. It takes time. The gas has to radiate away its thermal energy. In small halos, this happens relatively quickly. In large halos, it takes longer because the gas is hotter and more spread out. The rate at which gas cools and falls into the center of a halo sets the rate at which stars can form. Push that rate too high and you run into physical limits. Gas can only cool so fast. Radiation can only carry away energy so fast. Even if the dark matter halo is massive enough to hold billions of solar masses in gas, that does not mean the gas can turn into stars on a timescale of a few 100 million years. Modern galaxies form stars at rates of a few to a few tens of solar masses per year. The Milky Way, for example, forms about 2 solar masses worth of stars each year. At that rate, it would take 5 billion years to form 10 billion solar masses worth of stars. Some galaxies, called starburst galaxies, form stars much faster, up to a few hundred or even 1,000 solar masses per year. But starburst episodes do not last long. They burn through the available gas in a few tens of millions of years and then shut down. The early galaxies Webb is detecting would need to sustain star formation rates of hundreds to thousands of solar masses per year for hundreds of millions of years to build up the masses observed. That is not a starburst. That is a sustained industrial level of star formation, and it is unclear what could fuel it. One idea is that these early galaxies were sitting at the intersections of multiple dark matter filaments in the cosmic web. The cosmic web is the large-scale structure of the universe, a network of filaments and voids stretching across billions of light-years. Galaxies form at the nodes where filaments intersect, where the density of matter is highest. If an early galaxy happened to sit at a particularly rich node, it could have access to a continuous supply of gas streaming in along the filaments. This could sustain high star formation rates for extended periods. Some simulations show that the densest nodes in the early universe could funnel gas into galaxies at rates high enough to support star formation of several hundred solar masses per year. But even this has limits. The gas streaming in along filaments is not cold. It is shock heated as it falls into the halo, reaching temperatures of millions of degrees. Hot gas does not form stars. It has to cool first. The cooling time depends on the density and temperature of the gas. In massive halos, the cooling time can be hundreds of millions of years. You can speed it up by increasing the density or by adding cooling agents like heavy elements, but both of those require conditions that do not exist in the early universe. The gas is not dense enough, and the heavy elements have not been produced yet. This is the paradox. The galaxies exist. They are there, shining in the data, massive and chemically mature. But every step of the process that should have produced them takes longer than the time available. Star formation takes time, chemical enrichment takes time, halo growth takes time, gas cooling takes time. Add it all up, and you need at least 500 million to a billion years to produce a galaxy like Sears 1019. The universe gave it 300 million. Something is missing. Either there is a process we do not understand that accelerates growth in the early universe, or our models of star formation, halo growth, and chemical enrichment are fundamentally wrong. The cosmic age problem, as some astronomers are now calling it, is not a problem with the age of the universe itself. The universe is 13.8 billion years old. That number is well established, measured independently through multiple methods. The problem is with the relative ages of structures within the universe. How can a galaxy that looks like it should be a billion years old exist when the universe itself is only 300 million years old? How do you compress a billion years of evolution into 300 million? There is no clean answer yet. The models are being revised, parameters are being adjusted, new simulations are being run. But so far, nothing fully explains the data without invoking processes or conditions that we have no direct evidence for. The galaxies are telling us something. They are telling us that the early universe was more active, more efficient, more violent than we thought. They are telling us that our timeline is wrong, and they are forcing us to ask whether the rules we think govern galaxy formation are as universal as we assumed, or whether the early universe played by a different set of rules entirely. The evidence is mounting, the anomalies are multiplying, and the contradictions are becoming harder to ignore. The galaxies themselves told the first lie, or at least that is how it felt when the data started coming in. Because when you spend decades building a model of how the universe works, testing it against every observation you can gather, refining it until it predicts the large-scale structure of reality with stunning accuracy, and then a telescope points at the earliest moments of cosmic history and says the model missed by a factor of 10, it does not feel like a discovery, it feels like betrayal. But the galaxies were not lying. They were just sitting there, glowing quietly in the infrared, waiting for someone to look hard enough. And when Webb looked, it found three things that should not exist together in the same objects at the same time. Three anomalies so severe that each one on its own would have been uncomfortable. Together, they constitute what some researchers are now calling the most challenging discovery in the history of modern astronomy. The first anomaly is mass, pure, undeniable, impossible mass. When the James Webb Space Telescope completed its first comprehensive census of the early universe in 2024, the team catalogued roughly 300 galaxies at redshifts between 7 and 10. That corresponds to a look-back time of 500 to 700 million years after the Big Bang. 300 galaxies. That number alone was higher than expected. The lambda cold dark matter model predicted a few dozen at most, but the real shock was not the count, it was the weight. Some of these galaxies were enormous, not in physical size, though a few were surprisingly large, but in stellar mass. The amount of matter locked up in stars. When astronomers measured the brightness of these galaxies and ran the numbers through their models, accounting for distance and the stretching of light by cosmic expansion, they calculated masses that made no sense. 10 billion solar masses, 20 billion, in a few cases 30 billion. These were not small irregular blobs of a few million stars clumping together in the darkness. These were massive, luminous structures containing as many stars as the modern Milky Way, and they were sitting in an era when the universe was only 5% of its current age. To put that in perspective, imagine you plant a seed in your backyard. You water it, walk inside, and 20 minutes later you look out the window and there is a 100-foot oak tree standing where the seed was. Not a sapling, not a young tree, a fully mature oak with deep roots and thick branches. That is the scale of the problem. The Milky Way has spent 13 billion years building up its stellar mass through a combination of star formation and mergers with smaller galaxies. These early galaxies appear to have done the same thing in 500 million years. The timeline is compressed by a factor of 20. One galaxy in particular, flagged during the early observations, caught the attention of multiple teams. Its catalog designation is unremarkable, a string of letters and numbers that only an astronomer could love. But its properties were anything but. The galaxy sits at a redshift of roughly 9, placing it about 530 million years after the Big Bang. The spectral analysis revealed a stellar mass of approximately 10 billion solar masses. 10 billion. That is comparable to the Large Magellanic Cloud, one of the Milky Way's satellite galaxies. Except the Large Magellanic Cloud has had the entire history of the universe to build itself. This galaxy did it in 500 million years. The problem is not just that the galaxy is massive. The problem is that building that much mass requires a sustained rate of star formation that physics struggles to support. Stars form from gas. Gas has to cool before it can collapse. Cooling takes time. Once the gas collapses and stars ignite, the stars themselves start heating the surrounding gas with their radiation, making it harder for more stars to form. This is called feedback, and it is one of the main reasons star formation in modern galaxies is so inefficient. Only about 10% of the available gas actually turns into stars. The rest is either too hot, blown away by supernova explosions, or simply sitting around doing nothing. For a galaxy to reach 10 billion solar masses in 500 million years, it would need to form stars at an average rate of about 20 solar masses per year, sustained over the entire period. 20 solar masses per year is not outrageous. Starburst galaxies in the modern universe can hit rates of a few hundred solar masses per year during short, intense bursts of activity. But those bursts last only a few tens of millions of years before the galaxy runs out of gas or feedback shuts the process down. To sustain 20 solar masses per year for 500 million years with no breaks, you need a constant supply of fresh gas and a cooling mechanism efficient enough to keep the gas collapsing despite the intense radiation from all the young stars. In the early universe, where there were almost no heavy elements to act as coolants, that is a tall order. The lambda cold dark matter model accounts for this. It predicts that galaxies in the first few 100 million years should form stars quickly but inefficiently. The total stellar mass by 500 million years should be in the range of a few 100 million solar masses, maybe a billion if conditions are particularly favorable. Not 10 billion, not 20 billion, and certainly not 30 billion, which is what a few of the most extreme cases clocked in at. The observations were showing galaxies that were 5 to 10 times more massive than the models allowed. That is not a small discrepancy, that is a systematic failure of prediction. The second reaction from the community was skepticism. Maybe the mass estimates were wrong. Measuring the stellar mass of a galaxy 13 billion light-years away is not straightforward. You cannot count the stars one by one. You measure the galaxy's brightness, estimate how much of that light is coming from stars versus other sources, and then use models of stellar populations to convert brightness into mass. Each step involves assumptions. Small errors in those assumptions can lead to large errors in the final number. If the galaxies contained unusually luminous stars, or if some of the light was coming from an active supermassive black hole rather than stars, the mass estimates could be inflated. teams went back and checked. They used multiple methods to estimate the masses. They cross-referenced the photometric data with spectroscopic observations to rule out contamination from active black holes. They ran simulations with different stellar population models, varying the assumptions about the ages and compositions of the stars. The numbers shifted slightly, but not by much. Some of the galaxies did have active black holes contributing to their brightness, and after accounting for that, their stellar masses came down. But even after removing the most egregious cases, the excess remained. There were still far more massive galaxies than the models predicted. The observations were showing twice as many galaxies with masses above 1 billion solar masses as the lambda cold dark matter model allowed. Twice. That is not an error in measurement. That is a fundamental problem with the model. The third check was statistical. Maybe these galaxies were not typical. Maybe they were rare outliers, the result of unusually favorable conditions in particularly dense regions of the early universe. If you look hard enough, you can always find a few objects that push the boundaries of what is possible. The question is whether those objects are representative of the broader population or just flukes. The 2024 census answered that question. 300 galaxies. That is not a fluke. That is a population, and when you plot the distribution of stellar masses for those 300 galaxies and compare it to what the models predict, the difference is stark. The observed distribution is shifted toward higher masses by a factor of 5 to 10. There are too many massive galaxies, and they are too massive. The universe at 500 million years old was not supposed to look like this. Then came the second anomaly, metallicity. This one is quieter than the mass problem, less immediately obvious, but in some ways more troubling because it cuts deeper into the timeline. Metallicity, in astronomical terms, is the fraction of a star or galaxy that is made up of elements heavier than helium. Hydrogen and helium are primordial, created in the first few minutes after the Big Bang. Everything else, carbon, oxygen, nitrogen, iron, silicon, every element heavier than the second entry on the periodic table is produced inside stars through nuclear fusion. When stars die, they scatter those elements into space. The next generation of stars incorporates those elements, and when they die, they scatter even more. Over time, the metallicity of the universe increases generation by generation. In the first few 100 million years after the Big Bang, the metallicity should be extremely low, near zero. The first generation of stars, population 3, had no heavy elements at all. They were pure hydrogen and helium. When they exploded, they seeded the surrounding gas with traces of carbon, oxygen, and other elements, but only traces. The second generation population 2 stars had low metallicity, maybe a few hundredths of a percent by mass. It takes multiple generations of star formation and death to build up significant amounts of heavy elements. Our Sun, a population 1 star, has a metallicity of about 2%. That is the result of billions of years of stellar evolution, generation after generation enriching the gas. The Galaxies Webb found at 500 to 700 million years after the Big Bang should have metallicities close to zero, maybe a few tenths of a percent at most. That was the prediction. Spectroscopic observations revealed something else. When the near-infrared spectrograph split the light from these galaxies into its component wavelengths, the spectra showed clear emission lines corresponding to oxygen. Not faint traces, clear, strong lines. Oxygen is a heavy element produced in the cores of massive stars and ejected during supernova explosions. Detecting oxygen means that stars had already formed fused hydrogen into helium, helium into carbon, carbon into oxygen, lived their entire lives and died. All of that had to happen before the galaxy was observed, and the amount of oxygen detected was not trivial. One team analyzing a galaxy at a redshift of about 14 found oxygen lines strong enough to suggest a metallicity of roughly 1/10 of the solar value. 1/10. That means the gas in this galaxy had already been enriched to 10% of the level we see in our own solar neighborhood, a region that has spent 13 billion years accumulating heavy elements. This galaxy, at just under 300 million years old, was already a tenth of the way there. The only way that happens is if a large number of massive stars had already formed and exploded. Massive stars, the ones that produce oxygen, live for only a few million years. But you cannot have massive stars dying in large numbers unless you first have massive stars forming in large numbers. And you cannot have massive star formation unless you have gas to form them from. And that gas, in the very early universe, should be almost entirely hydrogen and helium, with no heavy elements to help it cool and collapse efficiently. This is the metallicity bottleneck. You need stars to produce heavy elements. You need heavy elements to make star formation more efficient. But in the beginning, you have neither. The first generation of stars has to form without heavy elements, and they do, but they form slowly and inefficiently. When they die, they enrich the gas slightly, making the second generation a bit easier to form. The second generation enriches the gas more, making the third generation easier still. It is a slow feedback loop, and it takes time, hundreds of millions of years. The standard models predicted that by 500 million years after the Big Bang, the metallicity of galaxies should be around 1/100th to 1/50th of the solar value. The observations are showing metallicities 5 to 10 times higher than that. Once again, the universe was ahead of schedule. The presence of oxygen is not just a chemical curiosity, it is a clock. Oxygen tells you that multiple generations of stars have already lived and died. That means the galaxy is not young, it is mature. Not mature in the sense of being old, because it is only a few 100 million years old, but mature in the sense of having already gone through the cycles of star formation, enrichment, and evolution that should take much longer. The chemistry does not match the age. The two are out of sync, and the gap is too large to explain away with small adjustments to the models. Some astronomers suggested that the metallicity might be coming from localized regions within the galaxies, hotspots where star formation was particularly intense. If you pack a lot of massive stars into a small volume, they can enrich the local gas very quickly through their collective supernova explosions. The oxygen lines could be coming from those hotspots rather than representing the metallicity of the galaxy as a whole. Follow-up observations tested that idea. Integral field spectroscopy, a technique that maps the spectrum of a galaxy point by point across its entire structure, revealed that the oxygen was not confined to small regions. It was distributed throughout the galaxy. The entire system had been enriched. That ruled out the hotspot explanation. The metallicity was real, widespread, and inconsistent with the timeline. Then came the third anomaly, morphology. The shape and structure of the galaxies themselves. This one blindsided the field because nobody was expecting it. The assumption going into Webb's observations was that early galaxies would be messy, irregular, chaotic. The first galaxies were supposed to be clumpy, disordered collections of stars held together loosely by gravity, still in the process of settling down. Modern galaxies, by contrast, are organized. Spirals have well-defined arms and central bulges. Ellipticals are smooth, symmetric, and dynamically relaxed. That organization takes time to develop. Galaxies grow by merging with smaller galaxies and by accreting gas from their surroundings. Each merger disrupts the structure, and it takes hundreds of millions of years for the system to settle back into an organized state. The early universe was supposed to be full of mergers, full of disruption, full of galaxies that had not yet figured out what shape they wanted to be. Webb found spirals, not clumpy, irregular blobs, spirals. Galaxies with clear spiral arms, central bulges, and organized disks of stars rotating in a coherent pattern. One galaxy in particular, nicknamed the Big Wheel by the team that discovered it, is a nearly perfect spiral sitting at a redshift of about 8.3. That places it roughly 600 million years after the Big Bang. The galaxy is 3 times larger in diameter than simulations predicted any galaxy at that distance could be. And it is not just large, it is structured. The spiral arms are well defined. The disk is thin and flat. The central bulge is prominent. This is not a galaxy in the process of forming. This is a galaxy that looks like it has been around for billions of years. The morphology problem is subtle but profound. Galaxy morphology is tied to dynamics. A spiral galaxy requires a rotating disk of gas and stars. For the disk to be thin and stable, the system has to be dynamically relaxed, meaning the stars and gas are moving in organized orbits rather than random chaotic paths. Relaxation takes time. When 2 galaxies merge, the merger scrambles the orbits of the stars. The system becomes disordered, puffed up, messy. It takes several orbital periods, hundreds of millions of years, for the stars to settle back into a coherent disk. The fact that Webb is finding organized spirals at 600 million years after the Big Bang means those galaxies have already been through the chaotic phase and come out the other side. They are post-relaxation. That should not be possible. There has not been enough time. Another galaxy catalogued as XMM-VD12075 pushed the problem even further. This galaxy sits at a look-back time of about 2 billion years after the Big Bang, not as early as some of the others, but still firmly in the era when galaxies were supposed to be young and messy. XMM-VD12075 is an elliptical, not just any elliptical. A dynamically mature, non-rotating elliptical galaxy with a smooth symmetric light profile and no signs of recent merger activity. Elliptical galaxies are thought to form through major mergers, violent collisions between 2 spiral galaxies that destroy the disks and leave behind a smooth, pressure-supported ball of stars. The merger process is chaotic and takes time. After the merger, the system has to relax, and relaxation in an elliptical galaxy is even slower than in a spiral because there is no organized rotation to help things settle. The stars are moving in random directions, and it takes a long time for those random motions to smooth out into a stable configuration. XMM-VD12075 reached full dynamical maturity in under 2 billion years. The Lambda cold dark matter model says that is not enough time. The galaxy should still be showing signs of the merger that created it. There should be tidal streams, asymmetries, evidence of recent disruption. There are none. The galaxy looks old, settled, finished. It is sitting in an era when it should still be under construction, and instead it looks like it has been sitting quietly for billions of years. The morphology does not match the age. Once again, the timeline is wrong. A 2023 study examined 6 galaxies at 500 million years after the Big Bang and found that all 6 were already organized, not irregular clumps, organized structures with clear signs of rotation and symmetry. The paper described them as already containing stars, as if that was somehow surprising. Of course they contain stars. That is what makes them galaxies. But the word choice reveals the discomfort. These galaxies were not supposed to be this put together this early. They were supposed to be proto-galaxies, messy precursors to the organized systems we see in the modern universe. Instead, they looked like finished products. The universe was skipping ahead in the textbook. The methods used to confirm these anomalies are worth understanding because they are what make the observations credible. Webb's near-infrared camera, NEIR-CAM, captures images at multiple wavelengths. By comparing the brightness of a galaxy in different filters, astronomers can estimate its redshift. This is called a photometric redshift, and it is fast but not perfectly accurate. To confirm the distance, they use spectroscopy. Webb's near-infrared spectrograph, NIR-SPEC, splits the light into a spectrum, revealing the positions of emission and absorption lines. Those lines are shifted toward the red end of the spectrum by a precise amount determined by the expansion of the universe. Measure the shift, and you have the redshift. Measure the redshift, and you have the distance. This is how every high redshift galaxy in Webb's catalog has been confirmed. The spectral lines also reveal the galaxy's chemistry. Oxygen emits light at specific wavelengths, so does carbon, nitrogen, and every other element. When those lines show up in a spectrum, you can measure their strength and calculate the abundance of each element. This is spectral line analysis, and it is one of the most powerful tools in astronomy. It does not just tell you what a galaxy is made of. It tells you the history of star formation in that galaxy, because the abundances of different elements reflect the number of generations of stars that have lived and died. Morphology is measured through imaging. High-resolution images reveal the structure of a galaxy, the distribution of light across its disk or bulge. When the light is concentrated in a central region with fainter arms or features extending outward, you have a spiral or an elliptical. When the light is irregular and clumpy, you have a disordered system. But morphology alone does not tell you if the structure is real or just a projection effect. To confirm that a spiral is actually rotating, you need kinematics. Integral field spectroscopy maps the velocity of gas and stars across the galaxy. One side of the disk is moving toward us, the other side is moving away. That shows up as a shift in the spectral lines, blue shifted on one side, red shifted on the other. This is called a rotation curve, and it is the signature of an organized disk. The Big Wheel galaxy has a clean rotation curve. The disk is rotating. The structure is real. The collective weight of these three anomalies is what makes the problem so severe. Any one of them, taken in isolation, could be explained as an outlier or a measurement error. Massive galaxies could form in rare, overdense regions. High metallicity could result from unusually efficient star formation in localized hotspots. Organized morphology could be a projection effect, a galaxy that looks organized from our viewing angle but is actually chaotic in 3 dimensions. But all 3 anomalies show up in the same galaxies. The massive galaxies have high metallicity. The galaxies with high metallicity have organized morphology. The organized spirals are massive and chemically enriched. The anomalies are correlated, and that correlation rules out most of the easy explanations. These are not flukes. These are not measurement errors. These are real galaxies with real properties that do not fit the models. By late 2024, the numbers were undeniable. The census was complete. 300 galaxies at redshifts between 7 and 10. Statistical analysis confirmed that the excess of massive galaxies was not a selection effect or an artifact of the survey design. The models predicted a few dozen galaxies above 1 billion solar masses at these distances. Webb found more than 100. After removing the cases where active black holes were inflating the brightness, after correcting for photometric redshift uncertainties, after applying every conservative assumption the teams could think of, the excess remained. 5 to 10 times more massive galaxies than the lambda cold dark matter model predicted. 5 to 10 times. The implications ripple outward. If galaxies can form this quickly, this massively, this efficiently, then the assumptions underlying the lambda cold dark matter model are wrong. Not slightly wrong, fundamentally wrong. Either the initial conditions of the universe were different than we thought, or the process of structure formation in the first few 100 million years operated by rules we do not understand. Dark matter might behave differently at high redshift. Star formation might be vastly more efficient in the early universe. The cooling mechanisms that regulate how gas collapses into stars might not work the way we think they do. Or there might be entirely new physics at play, processes that have no analog in the modern universe and only operated in the extreme conditions of the cosmic dawn. One astronomer, speaking at a conference in 2024, called it the most challenging discovery in the history of modern astronomy. That is not hyperbole. The stakes are enormous. The lambda cold dark matter model is the foundation of modern cosmology. It is the framework that explains the cosmic microwave background, the large-scale structure of the universe, the distribution of galaxies, the acceleration of cosmic expansion. If the model fails to explain the first few 100 million years, then either the model is incomplete or our understanding of the early universe is so far off that we are essentially starting over. The data from Webb is forcing that reckoning. The galaxies are there, they are massive, they are chemically enriched, they are organized, and they should not exist. The anomalies are not subtle, they are not marginal, they are glaring, systematic, and growing with every new observation. The universe at 500 million years old does not look like the universe the models predicted. It looks older, more developed, more complex. It looks like someone skipped a chapter and went straight to the ending, and if that is true, then everything we thought we understood about how galaxies form needs to be reconsidered from the ground up. The models were not supposed to break. That is the part that makes this uncomfortable. The lambda cold dark matter model, the framework that has guided cosmology for half a century, was not some rough sketch thrown together by theorists with too much coffee and not enough data. It was battle-tested. It had survived challenge after challenge. It explained the cosmic microwave background radiation with extraordinary precision. It predicted the large-scale structure of the universe, the distribution of galaxy clusters and voids across billions of light-years. It accounted for the acceleration of cosmic expansion driven by dark energy. It was not perfect, but it was robust. And then the James Webb Space Telescope pointed at the early universe, and the model started showing cracks. Not small hairline fractures that could be patched with minor adjustments. Deep structural cracks that suggested something fundamental was missing. By late 2024, the observations were undeniable. The galaxies were there, massive, chemically enriched, organized, sitting in an era when they had no business existing in that state. The anomalies were too large to ignore and too consistent to dismiss as flukes. The question facing the field was no longer whether the models were wrong. The question was how wrong they were and what needed to be fixed. And that question opened the door to a flood of new ideas, some of them radical, some of them speculative, all of them attempts to reconcile what Webb was seeing with what physics says should be possible. The Rulebook, as one astronomer put it, was being rewritten in real time. The first instinct was conservative. Maybe the models were not fundamentally broken, maybe they just needed fine-tuning. The lambda cold dark matter framework is built on a set of parameters, numbers that describe the density of matter, the rate of expansion, the strength of gravitational clustering. Adjust those parameters slightly, and the predictions change. If the initial density fluctuations in the early universe were a bit larger than we thought, structure would form faster. Dark matter halos would collapse earlier. Galaxies would have more time to grow. The timeline would open up, and the massive galaxies Webb found would fit comfortably within the extended window. The problem with that idea is the cosmic microwave background. The cosmic microwave background is a snapshot of the universe at 380,000 years old, frozen in the faint glow of radiation that has been traveling through space for more than 13 billion years. That radiation carries the imprint of the density fluctuations that seeded the formation of all structure in the universe. Galaxies, clusters, superclusters, all of it traces back to those tiny ripples in the primordial density field. And those ripples are measured precisely. The Planck satellite spent years mapping the cosmic microwave background with extraordinary accuracy, and the fluctuations it detected are exactly the size needed to produce the universe we see today, assuming the standard growth rate for structure formation. If you want structure to form faster, you need larger initial fluctuations. But larger fluctuations would show up in the cosmic microwave background as stronger variations in temperature from one patch of sky to another. The Planck data does not show that. The fluctuations are small, smooth, consistent with a universe that builds structure slowly over hundreds of millions of years. You cannot make the fluctuations larger without contradicting the cosmic microwave background observations. The parameters are locked in. There is no room to tweak them without breaking something else. So the conservative approach hit a wall. If the parameters cannot be adjusted, then something deeper has to give. Either the physics of how structure forms in the early universe is different than we thought, or the observations are telling us something we have not yet understood. The field split into camps, each pursuing a different line of attack. Some focused on star formation, some focused on dark matter. Some went even further, questioning whether the fundamental assumptions about how galaxies grow were correct at all. The star formation camp started with a simple observation. In the modern universe, only about 10% of the gas in a galaxy actually turns into stars. The rest either stays as gas, gets blown out by supernova explosions and stellar winds, or simply never collapses. That 10% efficiency is baked into the models. It is what sets the rate at which galaxies build up their stellar mass. But what if that efficiency was different in the early universe? What if the first few 100 million years were a period of unusually high efficiency, a brief window when conditions allowed gas to turn into stars much more rapidly than it does today? There are reasons to think this might be the case. The early universe had no heavy elements. That sounds like a disadvantage, and in some ways it is, but it also removes one of the main regulators of star formation. Heavy elements produce dust, and dust absorbs and re-radiates energy, cooling the gas and helping it collapse. But dust also blocks radiation from newly formed stars, creating a kind of negative feedback loop that limits how many stars can form at once. Without heavy elements, there is no dust. Without dust, the radiation from young stars can travel farther and ionize more gas, but the gas itself can also collapse more completely without being disrupted. The net effect is complicated, and simulations give different answers depending on the assumptions you plug in. Some suggest that star formation efficiency in the early universe could have been as high as 50% or more. That is 5 times higher than the modern value. If that is true, galaxies could build up mass much faster. The most extreme version of this idea involves what some researchers are calling dark stars, not stars made of dark matter, but stars powered by it. The hypothesis, proposed by a team at the University of Texas, suggests that in the very early universe, before the first normal stars ignited, there could have been a brief period when clouds of hydrogen and helium were dense enough and cool enough to trap dark matter particles in their cores. Dark matter particles, if they have the right properties, can annihilate when they collide with each other, converting their mass into energy. If a gas cloud trapped enough dark matter particles, the energy from annihilation could heat the cloud from the inside, preventing it from collapsing all the way into a normal star, but allowing it to shine with the energy of millions of suns. These hypothetical dark stars would be enormous. Calculations suggest they could reach masses of 10 million times the mass of the Sun or more, glowing with the light of an entire galaxy concentrated in a single object. And they would form early, possibly within the first 100 million years after the Big Bang, because they do not require the slow buildup of structure that normal stars need. A sufficiently dense cloud of gas and dark matter could collapse directly into a dark star without going through the usual stages of fragmentation and cooling. If dark stars existed, they could explain why the early galaxies Webb is detecting are so bright and so massive. The light might not be coming from billions of normal stars. It might be coming from a handful of dark stars, each one shining with extraordinary luminosity. The idea is speculative. Nobody has ever observed a dark star. Nobody knows if dark matter particles even have the properties needed to make this work. The hypothesis requires dark matter to annihilate efficiently, and most models of dark matter do not predict that. But the idea is not crazy. It fits within the bounds of known physics, and it solves multiple problems at once. It explains the brightness of early galaxies. It explains why they appear so massive when they might not actually contain that many normal stars. And it provides a mechanism for rapid early growth that does not require breaking the lambda cold dark matter model. The dark stars would be a transient phase, lasting only until normal star formation took over, which is why we do not see them in the modern universe. They would leave behind only their influence, a burst of early enrichment and structure that jump-started galaxy formation. The dark star hypothesis has its critics. One of the main objections is that even if dark stars existed, they should still show up in Webb's spectra. The light from dark matter annihilation would have a different signature than the light from normal stars, and spectroscopy should be able to distinguish between the two. So far, the spectra of the early massive galaxies look consistent with light from normal stars, not exotic dark matter-powered objects. That does not rule out dark stars entirely. It is possible that the dark stars contributed some of the light, but were not the dominant source. Or it is possible that the spectral signatures are being washed out by the presence of normal stars in the same galaxies. The jury is still out. Another approach focuses on black holes. Supermassive black holes, the kind that sit at the centers of galaxies and weigh millions or billions of times the mass of the Sun, are known to form early. We have detected quasars, the bright feeding signatures of supermassive black holes, at redshifts above 7, meaning they existed less than 1 billion years after the Big Bang. The question has always been how they got so big so fast. Black holes grow by eating matter, and the rate at which they can eat is limited by the radiation pressure of the infalling gas. Feed a black hole too fast, and the radiation pushes the gas away before it can fall in. This is the Eddington limit, and it sets a maximum growth rate. Even at the Eddington limit, a black hole starting from a stellar mass seed of 10 solar masses can only reach a few million solar masses in a few 100 million years. Some of the supermassive black holes detected at high redshift are already hundreds of millions of solar masses. They are too big for the timeline. One way around this is to start with a much bigger seed. Instead of forming from the collapse of a single massive star, what if some black holes formed directly from the collapse of entire gas clouds in the early universe? This is the direct collapse black hole hypothesis, and it has been around for more than a decade, but Webb's observations have brought it back into focus. Direct collapse black holes would form when a massive cloud of primordial gas weighing tens or hundreds of thousands of solar masses, collapses under its own gravity without fragmenting into smaller pieces. Normally, gas clouds fragment as they collapse, breaking apart into clumps that form individual stars. But if the gas is hot enough and smooth enough, it can collapse as a single coherent mass, bypassing the star formation phase entirely and collapsing directly into a black hole. The conditions for direct collapse are stringent. The gas has to be kept hot to prevent fragmentation, which means it has to be bathed in intense ultraviolet radiation from nearby stars. But at the same time, the gas cannot have too many heavy elements, because heavy elements would cool the gas and allow it to fragment. The sweet spot is narrow, but simulations suggest it could occur in certain regions of the early universe where the first generation of stars had already formed and were producing ultraviolet radiation, but the second generation had not yet enriched the gas with heavy elements. In those regions, massive gas clouds could collapse directly into black holes weighing 100,000 solar masses or more. Start with a seed that large, grow it at the Eddington limit, and you can reach hundreds of millions of solar masses within a few 100 million years. The math works. If direct collapse black holes were common in the early universe, they could explain both the early supermassive black holes and the massive early galaxies. A black hole weighing 100,000 solar masses sitting at the center of a young galaxy would be a powerful engine for growth. Gas falling into the black hole would heat up and emit intense radiation, ionizing the surrounding gas and triggering bursts of star formation. The black hole and the galaxy would grow together, feeding off the same reservoir of gas. The galaxy would appear massive and bright, not because it had spent hundreds of millions of years forming stars generation by generation, but because it had a head start, a massive central black hole that accelerated the entire process. Webb has found evidence that some of the early massive galaxies do harbor active supermassive black holes. The spectra show emission lines characteristic of gas being heated by a central black hole. But not all of them. Some of the massive galaxies appear to be genuine stellar systems with no obvious black hole activity. That suggests direct collapse black holes might be part of the story, but they are not the whole story. You still need a mechanism to explain why some galaxies without active black holes are so massive and so chemically enriched so early. The dark matter camp took a different approach. Instead of focusing on stars or black holes, they questioned whether dark matter itself might behave differently in the early universe than it does today. Dark matter is the scaffolding of cosmic structure. It clumps together under gravity, forming halos that pull in normal matter and seed the formation of galaxies. The lambda-cold dark matter model assumes that dark matter is cold, meaning it moves slowly compared to the speed of light. Cold dark matter clumps together efficiently, forming structure on all scales from small halos to giant clusters. But what if dark matter is not entirely cold? What if it has some small velocity, some warmth, that changes how it behaves in the first few 100 million years? Warm dark matter, as it is called, would still clump together, but it would smooth out structure on small scales. The smallest halos, the ones that form first in the cold dark matter model, would be suppressed. Larger halos would form more quickly because there would be less competition from the small ones. The net effect would be a shift toward earlier formation of massive structures. Some simulations of warm dark matter show that galaxies at high redshift could be more massive than in the standard cold dark matter model because the mass that would have gone into small halos gets funneled into larger ones instead. The timeline compresses and the early universe becomes more top-heavy, with fewer small galaxies and more massive ones. The problem with warm dark matter is that it struggles to explain the structure we see in the modern universe. Cold dark matter predicts a certain abundance of small halos and satellite galaxies around large galaxies like the Milky Way. Warm dark matter predicts fewer. Observations of the Milky Way and other nearby galaxies show that the abundance of small satellites is consistent with cold dark matter, not warm. There is some wiggle room in the data, and a few researchers have argued that a very slight warmness, just enough to change the early universe without disrupting the modern one, might be possible. But most cosmologists are skeptical. The evidence for cold dark matter in the local universe is strong, and abandoning it to fix the early universe feels like robbing Peter to pay Paul. Another dark matter idea involves self-interacting dark matter. In the Standard Model, dark matter particles do not interact with each other except through gravity. They pass through each other like ghosts. But what if they do interact, weakly through some unknown force? Self-interacting dark matter would behave almost identically to standard cold dark matter on large scales, but on small scales, in the dense cores of halos, the interactions would matter. Collisions between dark matter particles would transfer energy, puffing up the cores of halos and changing how they collapse. Some simulations suggest that self-interacting dark matter could lead to faster halo growth in the early universe, allowing galaxies to form more massive structures more quickly. The challenge with self-interacting dark matter is the same as with warm dark matter. It is hard to tune the interaction strength to fix the early universe without breaking the modern universe. Too much interaction and the cores of dark matter halos become too diffuse, inconsistent with observations of galaxy rotation curves and gravitational lensing. Too little interaction and the effect is negligible. The parameter space is narrow, and it is not clear that a model exists that fits both the high redshift observations from Webb and the low redshift observations from Hubble and ground-based telescopes. A more radical approach questions whether the lambda cold dark matter model is correct at all. Some researchers have started to revisit alternative cosmologies, models that change the fundamental assumptions about how the universe expands or how gravity works on large scales. One such model is called early dark energy. The idea is that in addition to the dark energy we know exists today, accelerating the expansion of the universe, there was a second form of dark energy that existed only in the early universe. This early dark energy would have provided an extra push, accelerating the expansion briefly during the first few 100 million years before decaying away. The extra expansion would stretch out the density fluctuations, making structure formation more efficient in certain regions. Galaxies would form earlier and grow faster, and the universe at high redshift would look more developed than the Standard Model predicts. Early dark energy is not a new idea. It was proposed more than a decade ago as a possible solution to a different problem, the Hubble tension, a disagreement between different methods of measuring the rate of cosmic expansion. The idea did not gain much traction at the time because it required fine-tuning the properties of the early dark energy to fit the data, and fine-tuning is generally viewed with suspicion in physics. But Webb's observations have brought it back into the conversation. If early dark energy can explain both the Hubble tension and the early massive galaxies, it might be worth a second look. The challenge is that early dark energy affects the cosmic microwave background, and any model has to fit the Planck data. So far, no model of early dark energy has done that convincingly without introducing new problems elsewhere. Then there are the outliers, the ideas that sit at the edge of respectability. Some researchers have suggested that the speed of light might have been different in the early universe, faster than it is today, which would change the rate at which information and energy could propagate through space and potentially accelerate structure formation. Others have proposed modifications to general relativity, changes to the way gravity works on cosmological scales that would allow structure to collapse more quickly in the early universe without contradicting observations in the modern universe. These ideas are controversial. They challenge foundational principles of physics, and most physicists are reluctant to abandon those principles without overwhelming evidence. The bar for accepting a modification to general relativity or a variation in the speed of light is extraordinarily high, and so far the evidence from Webb, while surprising, has not cleared that bar. But the fact that these ideas are being discussed at all is a measure of how unsettled the field has become. Before Webb, the lambda cold dark matter model was secure. It had its puzzles, but they were viewed as details to be worked out within the framework, not threats to the framework itself. After Webb, that security is gone. The observations are forcing physicists to consider possibilities they would have dismissed a few years ago. The models are being stress-tested in ways they have never been tested before, and some of them are cracking. One of the more sobering possibilities is that the observations are telling us something we do not yet have the theoretical tools to understand. The history of physics is full of moments like this. Observations that did not fit the models, anomalies that accumulated until the weight of evidence forced a paradigm shift. The motion of Mercury's orbit did not fit Newtonian gravity. Einstein's general relativity explained it. The black-body spectrum of thermal radiation did not fit classical physics. Quantum mechanics explained it. The expansion of the universe did not fit the static cosmology of the early 20th century. The Big Bang model explained it. Each time, the solution required new physics, a deeper understanding of the underlying principles governing reality. Webb's observations might be pointing toward another such moment. The galaxies are there, the mass is real, the chemistry is real, the structure is real, and the models do not explain them, not with small adjustments, not with fine-tuning. The discrepancies are too large. Something fundamental is missing, and until we figure out what it is, we are in a state of uncertainty. That uncertainty is uncomfortable, but it is also exciting. It means the field is alive, grappling with data that challenges assumptions, forced to innovate and reconsider and explore new ideas. The rulebook is being rewritten, and nobody knows yet what the new rules will look like. The interdisciplinary nature of the problem is worth noting because it highlights how deeply the early universe connects different branches of physics. Cosmology, the study of the universe as a whole, overlaps with astrophysics, the study of stars and galaxies, which overlaps with particle physics, the study of the fundamental building blocks of matter. Dark stars require understanding dark matter particles. Direct collapse black holes require understanding gas dynamics and radiation physics. Self-interacting dark matter requires understanding particle interactions. Early dark energy requires understanding quantum field theory and the behavior of scalar fields in curved spacetime. The questions Webb is raising cannot be answered by cosmologists alone. They require input from particle physicists, nuclear physicists, computational scientists, and theorists working on the foundations of quantum mechanics and general relativity. Some of the most promising work is happening at the intersection of these fields. Teams are running simulations that combine cosmological structure formation with detailed models of star formation, chemical enrichment, and black hole growth. These simulations are computationally expensive, requiring supercomputers to track the evolution of millions of particles over billions of years of cosmic time. But they are producing results that can be compared directly to Webb's observations. When the simulations match the data, it suggests the underlying physics is correct. When they do not match, it points to where the models need to be revised. As of 2025, none of the simulations fully explain Webb's observations. The best models can reproduce some of the features, the mass or the metallicity or the morphology, but not all three at once in the same objects. That suggests the solution will require multiple changes, not just one. Faster star formation, more efficient gas cooling, earlier dark matter halo collapse, perhaps a contribution from direct collapse black holes or dark stars. The answer, when it comes, will likely be a combination of effects, each one contributing a piece of the puzzle. The observational side is also advancing. Webb is still in its early years of operation, and new data is coming in steadily. Larger surveys, covering more of the sky and reaching even higher redshifts, are planned. The goal is to build a complete census of galaxies in the first billion years of cosmic history, to map out not just the most massive objects, but the full distribution of masses, metallicities, and morphologies. That distribution will be the key to distinguishing between different models. If the excess of massive galaxies is concentrated in certain regions of the sky, it might point to localized overdensities in the early universe. If it is spread out uniformly, it suggests a more fundamental change to the global star formation efficiency or dark matter properties. Spectroscopy will play a critical role. Photometric observations can flag distant candidates, but spectroscopy is what confirms them and reveals their properties. Webb's near-infrared spectrograph is powerful, but it is also slow. Each spectrum requires hours of observation time, and the telescope can only observe one or a few galaxies at a time. Future instruments, both on Webb and on other telescopes, are being designed to speed up this process, allowing astronomers to gather spectra for hundreds or thousands of galaxies in a single observing campaign. That kind of statistical power will make it possible to test models much more rigorously than is currently feasible. There is also the question of whether some of the early massive galaxies are being misinterpreted. Observational bias is always a concern. Webb is biased toward detecting bright objects, and bright objects are not necessarily massive. A galaxy with an active supermassive black hole at its center can appear extremely bright without containing many stars. Some of the early candidates flagged as massive galaxies have turned out, on closer inspection, to be quasars or galaxies dominated by black hole emission rather than starlight. This does not mean the excess of massive galaxies is an illusion. It just means that not every bright object at high redshift is what it first appears to be. Follow-up spectroscopy is essential to weed out the false positives and build a clean sample of genuine massive stellar systems. Even accounting for that, the excess remains. The number of confirmed massive galaxies is still higher than the models predict, and the properties of those galaxies, the metallicity, the morphology, the sheer presence of organized structure, are inconsistent with the standard timeline. The observations are robust. The challenge is figuring out what they mean. The field is in flux. Papers are being written at a furious pace. Conferences are dominated by debates over the meaning of Webb's data and the viability of different theoretical models. The tone is one of cautious excitement mixed with genuine uncertainty. Nobody knows yet which direction the solution will come from. It might be faster star formation. It might be direct collapse black holes. It might be a tweak to dark matter properties or an entirely new form of energy in the early universe. Or it might be something nobody has thought of yet, a mechanism that will only become clear once more data comes in and more simulations are run. What is clear is that the lambda-cold dark matter model as it stands is incomplete. It works for the modern universe. It works for the cosmic microwave background, but it does not work for the first few 100 million years, and that is a problem that cannot be ignored. The early universe is where the rules were set, where the initial conditions were laid down, where the seeds of everything we see today were planted. If we do not understand that era, we do not fully understand the universe. Webb has given us a window into that era, and the view is unsettling. The universe looks older than it should, more developed than it should, more complex than it should, and until we figure out why, the rulebook remains open, waiting for someone to write the next chapter. The models were not just incomplete, they were built on assumptions we never thought to question. For half a century, cosmology has rested on a foundation so fundamental, so seemingly self-evident, that most scientists did not even think of it as an assumption. It was just the way things were. The universe is uniform. Matter is distributed roughly evenly across vast scales. The laws of physics work the same way everywhere. Look in any direction, travel to any point in space, and on average you will see the same thing. Galaxies clustered into filaments and voids, stars forming and dying. The expansion of space carrying everything apart at a rate that depends only on distance, not on direction. This is the cosmological principle, and it is more than just an observation. It is the scaffolding on which the entire standard model of cosmology is built. Without the cosmological principle, the equations do not work. General relativity, Einstein's theory of gravity, describes how matter and energy curve space-time. But the equations are ferociously complicated, and solving them requires simplifying assumptions. The cosmological principle provides those assumptions. If the universe is uniform on large scales, you can treat it as a smooth fluid, ignore the small-scale clumpiness of individual galaxies, and solve for the overall expansion. That solution gives you the Friedmann equations, the mathematical foundation of the Big Bang model. Those equations tell you how fast the universe is expanding, how its expansion rate changes over time, and how the density of matter and energy evolves as space stretches. Everything from the age of the universe to the distance to the farthest galaxies depends on those equations being correct. And those equations depend on the cosmological principle being true. The principle is not controversial. Observations have supported it for decades. Look at the cosmic microwave background, and you see a nearly uniform glow in every direction, variations of only one part in 100,000. Look at the distribution of galaxies across billions of light years, and you see structure, yes, but structure that averages out to uniformity when you zoom out far enough. The universe, on scales larger than a few 100 million light-years, looks the same no matter where you are or which direction you look. Cosmologists have tested this. They have mapped the positions of millions of galaxies, measured the clustering, calculated the statistical properties, and confirmed that the cosmological principle holds. It is one of the most thoroughly validated assumptions in all of physics. Until James Webb pointed at the early universe and found that the first few 100 million years do not look uniform at all. The galaxies Webb detected at redshifts above 10 are not evenly distributed. They are not randomly scattered across the sky the way the cosmological principle says they should be. They are clustered, concentrated in certain regions. Some patches of sky contain far more massive galaxies than others, and the regions with the most massive galaxies are not the regions where the cosmic microwave background shows the strongest density fluctuations. The two maps do not line up. The seeds of structure visible in the cosmic microwave background at 380,000 years after the Big Bang do not predict where the massive galaxies are sitting at 300 million years. The correlation is weak. In some cases, it is non-existent. That is a problem. If the cosmological principle holds, the seeds in the cosmic microwave background should predict where galaxies form. The densest regions at 380,000 years should become the densest regions at 300 million years. Matter flows from low-density regions into high-density regions under gravity. The rich get richer. The principle is straightforward, and it has worked beautifully for the modern universe. But the early universe, as seen by Webb, does not follow the script. The galaxies are forming in places they should not be, in numbers they should not reach, and the uniformity that the cosmological principle promises is nowhere to be found. Some researchers have started to ask whether the cosmological principle breaks down at high redshift, not because the laws of physics are different, but because the conditions in the early universe are so extreme that the assumption of uniformity does not apply yet. The cosmic microwave background shows the universe at 380,000 years, and at that moment it is uniform, nearly perfectly so. But between 380,000 years and 300 million years, something happens. Structure begins to form. Dark matter halos collapse. Gas falls into those halos. The universe transitions from smooth to clumpy, and during that transition, the distribution of matter might not be uniform. Some regions might get a head start. Random fluctuations, amplified by the chaotic dynamics of early structure formation, could produce pockets of the universe where galaxies form earlier and grow faster than the average. Those pockets would look like violations of the cosmological principle, but they would not be violations of physics. They would just be statistical outliers, rare but allowed. The problem with that explanation is scale. If the massive early galaxies were confined to a single small region of the sky, you could argue they are a local anomaly, a statistical fluke that does not challenge the overall uniformity of the universe. But they are not confined. Webb has surveyed multiple fields, regions of the sky separated by billions of light-years in the modern universe, and the excess of massive galaxies shows up everywhere. Not at the same density in every field, but consistently enough that it cannot be dismissed as a fluke. The early universe, at least the parts of it we can see, was systematically more developed than the cosmological principle predicts. That systematic excess is what makes the discovery so unsettling. It is not an outlier, it is a pattern, and patterns demand explanations. One possibility that keeps surfacing is that the expansion rate of the universe in the first few 100 million years was different than we thought. Not slightly different, significantly different. The expansion rate is described by a number called the Hubble parameter, and it changes over time as the universe ages. In the early universe, when matter was dense and gravity was strong, the expansion was slower. As the universe aged and dark energy began to dominate, the expansion accelerated. The lambda cold dark matter model calculates the expansion history by solving the Friedmann equations with the measured values of matter density, dark energy density, and the initial conditions from the cosmic microwave background. The result is a smooth curve that describes how the Hubble parameter evolved over the past 13.8 billion years. That curve predicts how far light from distant galaxies has traveled, and how old those galaxies are when we observe them. If the curve is wrong, the distances are wrong. If the distances are wrong, the ages are wrong. And if the ages are wrong, the timeline for galaxy formation changes. The Hubble constant, the value of the Hubble parameter today, has become one of the most contentious numbers in cosmology. Two independent methods for measuring it give different answers. The first method uses the cosmic microwave background. The Planck satellite measured the temperature fluctuations in the cosmic microwave background with extraordinary precision, and from those measurements, physicists extracted the values of the fundamental parameters describing the universe. Plug those parameters into the Friedmann equations, run the clock forward 13.8 billion years, and you get a prediction for the Hubble constant today. The answer is about 67 kilometers per second per megaparsec. For every 3.26 million light-years you look outward, galaxies are receding 67 kilometers per second faster. The second method measures the distances and velocities of galaxies directly. Astronomers use a technique called the cosmic distance ladder. starting with nearby stars whose distances can be measured precisely, then stepping outward to more distant galaxies using those stars as calibration. Combine the distances with the velocities measured from the redshifts of the galaxies, and you get the Hubble constant. The answer from this method is about 73 kilometers per second per megaparsec, not 67, 73. 6 kilometers per second per megaparsec might not sound like much. It is less than 10%. But in a field where measurements are precise to within 1 or 2%, a 6 kilometer per second per megaparsec gap is enormous, and it has been growing. As the measurements have gotten more precise, the discrepancy has not gone away. It has gotten worse. By 2024, the statistical significance of the tension had reached 5 sigma, the threshold physicists use to declare a discovery. This is not a fluke. This is a real disagreement between two methods that should give the same answer, and nobody knows which one is right. If the local measurement is correct, and the Hubble constant today is 73 instead of 67, then the expansion history of the universe is different than the Planck data predicts. The universe has been expanding faster than we thought, which means it took less time to reach its current size, which means the universe is younger than 13.8 billion years, not much younger. Maybe 13.2 or 13.4 billion years, but younger. And if the universe is younger, then the timeline for everything that happened in the early universe is compressed. The first stars had to form earlier. The first galaxies had to grow faster. The anomalies Webb is seeing become even harder to explain because there is even less time available. On the other hand, if the cosmic microwave background measurement is correct, and the Hubble constant today is 67, then the local measurements are wrong. Something about the cosmic distance ladder is biased. Maybe the calibration stars are not as well understood as we think. Maybe the distances to nearby galaxies are off by a small but systematic amount. Maybe there is some effect, dust absorption or gravitational lensing or something else that is skewing the measurements. But if that is the case, nobody has found it yet. The teams measuring the local Hubble constant have checked and rechecked their methods. They have used different types of stars, different calibration techniques, different telescopes. The answer keeps coming out the same: 73. The discrepancy is stubborn, and it refuses to go away. The Hubble tension, as it is called, might be connected to the early massive galaxies. If the expansion rate in the early universe was higher than the standard model predicts, structure would form faster. Dark matter halos would collapse earlier. Galaxies would have more time to grow, even though the overall age of the universe is slightly younger. The extra expansion would stretch out the density fluctuations in ways that could amplify their growth. Some models of early dark energy, a hypothetical form of energy that existed only in the first few 100 million years, predict exactly this: a brief burst of accelerated expansion, followed by a decay back to the standard expansion rate. The burst would leave subtle imprints in the cosmic microwave background, too small to have been detected by Planck, but possibly within reach of future experiments. And it would change the timeline just enough to make the early massive galaxies fit. Early dark energy is not the only possibility. Another idea involves a change in the strength of gravity in the early universe. General relativity predicts that gravity behaves the same way at all times and in all places. But what if that prediction is wrong? What if gravity was slightly stronger in the first few 100 million years, just enough to make dark matter halos collapse faster and pull in gas more efficiently? The change would not need to be large. A few percent would be enough. And as the universe aged and the density dropped, gravity would relax back to the strength we measure today. This is speculative, verging on radical, but it is not crazy. General relativity is a classical theory, and we know it breaks down at the smallest scales where quantum mechanics takes over. Nobody has successfully combined general relativity with quantum mechanics into a single unified theory, and it is possible that the early universe, with its extreme densities and temperatures, is a regime where the cracks in general relativity start to show. Modifying gravity is not something physicists do lightly. General relativity is one of the most successful theories in the history of science. It has passed every test thrown at it for more than a century: the orbit of Mercury, the bending of light around the Sun, gravitational waves from colliding black holes, the expansion of the universe. Every prediction has been confirmed, often with stunning precision. To suggest that general relativity might need modification is to suggest that one of the pillars of modern physics might be incomplete. That is a high bar, and the evidence from Webb, while surprising, has not cleared it yet. But the fact that the idea is being discussed at all shows how seriously the field is taking the anomalies. When your models fail by a factor of 5 to 10, you have to consider possibilities you would have dismissed a few years ago. Then there is the question of seeds. How did the massive early galaxies get started? What provided the initial boost that allowed them to grow so quickly? In the standard model, galaxies grow from small fluctuations in the density of matter. Regions that are slightly denser than average pull in more matter through gravity, becoming even denser, which pulls in even more matter. It is a runaway process, but it takes time. The initial fluctuations in the cosmic microwave background are tiny, 1 part in 100,000. Growing those tiny fluctuations into galaxies weighing billions of solar masses requires hundreds of millions of years of steady gravitational collapse. The process cannot be rushed, or at least it should not be able to be rushed, unless the seeds were not tiny fluctuations but something much larger. Primordial black holes that formed in the first fraction of a second after the Big Bang, are one candidate. In the chaotic environment of the early universe, before the cosmic microwave background was even released, there were brief moments when the density of matter varied wildly from place to place. In the densest regions, the density could have been so high that the matter collapsed directly into black holes without ever forming stars or galaxies first. These primordial black holes would have been massive from the start, possibly weighing thousands or even millions of times the mass of the Sun. If they existed, they would have acted as seeds for galaxy formation, pulling in gas and dark matter much more efficiently than a normal density fluctuation could. The idea is not new. Primordial black holes have been proposed as candidates for dark matter, though most of the parameter space for that idea has been ruled out by observations. But even if primordial black holes do not make up all of dark matter, they could still exist in small numbers, scattered throughout the universe. And if a few of them happen to sit in regions that were already slightly overdense, they could have jump-started galaxy formation in those regions, giving the galaxies a head start that allowed them to grow into the massive structures Webb is detecting. The problem with primordial black holes is that we have no direct evidence they exist. Nobody has ever detected one. The only way to confirm their existence would be to see their gravitational effects, either through lensing of background light or through the ripples they create in space-time when they merge with other black holes. Gravitational wave observatories like LIGO have detected dozens of black hole mergers, but all of them involve black holes that clearly formed from the collapse of massive stars, not from the early universe. If primordial black holes exist, they are either very rare or hiding in a mass range that has not been probed yet. Another possibility involves supermassive dark matter particles, hypothetical particles much heavier than any normal matter. In most models of dark matter, the particles are light, weighing less than a proton. But some theories predict that dark matter could come in multiple varieties, including a very heavy component with particles weighing thousands or even millions of times more than a proton. These supermassive particles would behave differently than normal dark matter. They would clump together more tightly, forming dense cores in the centers of dark matter halos. Those cores could act as seeds for galaxy formation, much like primordial black holes, but without requiring the extreme conditions needed to form black holes in the first place. The supermassive dark matter particles would just be sitting there, waiting for gas to fall in and start forming stars around them. The challenge with supermassive dark matter is that it has no observational support. It is a theoretical construct, invented to solve problems like the one Webb is revealing. That does not make it wrong, but it does make it speculative. Physicists are reluctant to invoke new types of particles unless there is clear evidence they are needed. So far, the evidence from Webb, while puzzling, has not forced that step. The field is still exploring whether known physics pushed to its limits can explain the observations before jumping to exotic new particles. There is also the philosophical angle. If the early universe was fundamentally different than we assumed, what does that mean for our understanding of the Big Bang itself? The Big Bang is not just a theory of how the universe began, it is a framework for understanding time, space, causality, the very structure of reality. The idea is that the universe started in a state of infinite density and temperature, and everything we see today, every galaxy, every star, every atom, emerged from the expansion and cooling of that initial state. The cosmic microwave background is the fossil record of that moment, a snapshot of the universe when it was 380,000 years old, frozen in radiation. Before that, the universe was opaque, too hot for light to travel freely. And before that, in the first fractions of a second, the conditions were so extreme that the laws of physics as we know them break down. We can describe what happened back to about 1/1,000,000,000th of a second after the Big Bang using known physics. Before that, we are guessing. The standard story is that the universe went through a brief period of exponential expansion called inflation in the first tiny fraction of a second. Inflation stretched the universe from something smaller than an atom to something larger than a grapefruit in less time than it takes light to cross the width of a proton. That rapid expansion smoothed out the universe, erasing any large-scale structure that might have existed before, and leaving behind only tiny quantum fluctuations that would later grow into galaxies. Inflation explains why the universe is so uniform, why the cosmic microwave background looks the same in every direction, and why the geometry of space is flat rather than curved. It is one of the most successful ideas in cosmology, and it has been tested in multiple ways, all of which support the basic picture. But inflation is not a complete theory, it is a framework, a description of what happened, not an explanation of why it happened or what caused it. There are dozens of different models of inflation, each one making slightly different predictions, and we do not know which one, if any, is correct. The field that drove inflation, the inflaton field, has never been detected. Its properties are unknown. Its connection to other fields in particle physics is speculative. Inflation works, in the sense that it explains the observations, but it is not understood. It is a placeholder, a box labeled solution to be determined later. What if the early massive galaxies are telling us that the box needs to be opened? What if inflation did not produce a perfectly smooth universe, but left behind larger fluctuations than we thought, fluctuations that were too subtle to show up in the cosmic microwave background, but strong enough to seed the formation of massive galaxies earlier than the standard model predicts? Some models of inflation allow for this. They predict that the fluctuations are not strictly uniform, but have a small amount of non-Gaussianity. meaning the distribution of fluctuations is slightly skewed toward larger values in rare regions. Those rare regions would be the places where galaxies form first and grow fastest. The bulk of the universe would look normal, consistent with the cosmic microwave background, but a small fraction of it, the tail of the distribution, would be more developed. Webb might be seeing that tail. Non-Gaussian fluctuations are hard to detect. The cosmic microwave background measurements from Planck are consistent with Gaussian fluctuations to high precision, but they do not rule out small amounts of non-Gaussianity. Future experiments with better sensitivity might be able to detect the signature if it is there. In the meantime, the early massive galaxies are indirect evidence that something about the initial conditions was not as simple as the standard models assume. There is also the multiverse. The idea that our universe is not the only one, that the Big Bang which created our universe was just one event in a much larger structure, a meta-universe or multiverse where Big Bangs happen all the time, creating countless separate universes with different properties. This is speculative, sitting at the edge of what most physicists consider legitimate science. The multiverse is not directly testable, because by definition, other universes are beyond our ability to observe. But some versions of inflation naturally produce a multiverse. If the inflaton field that drove inflation is quantum in nature and quantum fields can fluctuate, then different regions of the inflaton field could have inflated at different rates, creating separate bubble universes, each one with its own set of physical laws and initial conditions. If the multiverse is real, our universe is just one bubble in a much larger foam. The properties we observe, the density of matter, the strength of gravity, the rate of expansion, might not be fundamental. They might just be the particular set of values that happened to occur in our bubble. Other bubbles would have different values. And if the values in our bubble are slightly different than we think, if the initial conditions were not set by pure randomness but influenced by the larger multiverse structure, then the early universe might behave in ways that the standard single universe models do not predict. The massive early galaxies could be a signature of that influence, a hint that our universe did not start from a perfectly smooth blank slate but inherited some structure from the larger multiverse. This is where the science shades into philosophy. The multiverse is not a testable prediction in the traditional sense. You cannot build an experiment to detect another universe. But the idea is taken seriously by some of the best theoretical physicists in the world because it emerges naturally from certain extensions of known physics. Whether it is true or not, whether it even makes sense to call it a scientific hypothesis, is a debate that has been going on for decades and shows no signs of resolving. What Webb's observations add to that debate is a concrete anomaly, a set of data that does not fit the standard models and might require rethinking the nature of the Big Bang itself. The massive early galaxies do not prove the multiverse exists, but they do suggest that our understanding of the universe's beginning is incomplete. And if the beginning is more complex than we thought, then the multiverse, or something like it, moves from the realm of wild speculation to the category of ideas worth exploring. The expansion of the universe is tied to all of this. If the Hubble constant is higher than the cosmic microwave background predicts, the universe is expanding faster than it should. If the early universe was expanding faster, the timeline compresses and structure has to form more quickly. If structure forms more quickly, the lambda cold dark matter model needs revision. And if the model needs revision, the assumptions underlying it, including the cosmological principle, come into question. The chain of logic is tight, and each link depends on the others. Break one link, and the whole structure wobbles. The distance to the farthest galaxies is another piece of the puzzle. When we say a galaxy is 13.5 billion light-years away, we are using a measure called look-back distance, the distance the light has traveled. But the galaxy itself is not 13.5 billion light-years away anymore. Because space has been expanding while the light was traveling, the galaxy is now much farther. The proper distance, the actual distance to the galaxy today, is closer to 33 or 34 billion light-years. That is why the observable universe has a radius of 46 billion light-years, even though the universe is only 13.8 billion years old. Space itself has been stretching, carrying distant objects away from us faster than light can travel. This is not a violation of relativity. Nothing is moving through space faster than light. Space itself is expanding, and objects embedded in that space are being carried along for the ride. Understanding this distinction is critical for interpreting Webb's observations. The galaxies we are seeing at high redshift are not where they appear to be. We are seeing them as they were, not as they are. The light left those galaxies more than 13 billion years ago, and in the time since, those galaxies have aged, evolved, merged with other galaxies, and moved farther away. We will never see what they look like today. The light from their present state will not reach us for tens of billions of years, long after the sun has died and the Earth is gone. We are looking at ghosts, frozen images of objects that no longer exist in the form we see them. That ghostliness is part of what makes the early universe so hard to study. We are not observing a snapshot of a single moment. We are observing a patchwork of different moments, stitched together by the accidents of distance and light travel time. The galaxies at redshift 14 are being seen as they were 290 million years after the Big Bang. The galaxies at redshift 10 are being seen as they were 500 million years after the Big Bang. The galaxies at redshift 5 are being seen as they were 1 billion years after the Big Bang. Each redshift corresponds to a different era, and the story we are trying to reconstruct is spread across those eras, piece by piece, with gaps and uncertainties at every step. The early massive galaxies are forcing cosmologists to confront the possibility that the story they have been telling is incomplete. Not wrong, necessarily, but missing chapters. The lambda cold dark matter model describes the universe as it has existed for the past 13 billion years with remarkable accuracy. It predicts the clustering of galaxies, the distribution of dark matter, the properties of the cosmic microwave background. It works, but it was built on observations of the modern universe and extrapolations backward in time based on the assumption that the same processes operated throughout history. The assumption was reasonable. It was the best anyone could do with the data available, but it was still an assumption. And Webb is now showing that the first few 100 million years might not have followed the same rules. That does not mean the Big Bang is wrong. It means the details of what happened immediately after the Big Bang, the processes that turned a smooth, nearly uniform fog of hydrogen and helium into the first stars and galaxies, are more complicated than the models assumed. The fabric of time, the timeline that connects the Big Bang to the present, is being stretched and pulled by the observations, and the neat linear progression from simple to complex, from small to large, from primitive to mature, is starting to look less like a law of nature and more like a rough approximation that worked well enough until someone looked closely at the edges. The edges are where the cracks show. And Webb is looking at the edges with a clarity no telescope has ever had before. The data is clean, the observations are repeatable, the anomalies are real, and the field is being forced to reckon with the possibility that the universe's beginning, the moment everything started, might be stranger and more complex than anyone imagined. The models are being rewritten, the assumptions are being questioned, And the universe, as it always does when we look closely enough, is refusing to behave the way we told it to. The field is not broken, it is being rebuilt. That distinction matters because what is happening right now in labs and observatories and university offices scattered across every continent is not the collapse of cosmology. It is the messy, uncomfortable, exhilarating process of a science confronting data that refuses to fit the old boxes and being forced to build new ones. The James Webb Space Telescope has been operational for less than 3 years, and in that time it has delivered more challenges to the standard model of cosmology than the previous 2 decades combined. The early massive galaxies are not going away. They are not measurement errors. They are not flukes. They are real objects with real properties, sitting in an era when they should not exist in that form. And every new observation Webb makes adds another layer to the puzzle. The question facing astronomers in 2025 is not whether the models need to change. The question is how much they need to change and how long it will take to figure out the right direction. The follow-up observations are already underway. Webb's first 3 years were just the beginning. The telescope was designed to operate for at least 10 years, possibly longer if the fuel reserves last and the instruments hold up. NASA and the European Space Agency have committed to continued deep field surveys, programs designed to push Webb's sensitivity to its absolute limits and map the early universe in unprecedented detail. The JADES program, the collaboration that discovered some of the most distant and most massive galaxies, is expanding. Phase 2 of the survey, scheduled to run through 2026, will cover a larger area of sky and go even deeper, targeting galaxies at redshifts above 15. Redshift 15 corresponds to a look-back time of about 270 million years after the Big Bang. If galaxies exist at that distance, and there is every reason to think they do, they will be among the first structures to form in the entire universe. Finding them, measuring their masses, analyzing their chemistry will tell us whether the anomalies Webb has already detected are the tip of the iceberg or just rare outliers. The CR survey, another major collaboration, is also continuing. The Cosmic Evolution Early Release Science program has already catalogued hundreds of high redshift galaxies, and the team is now focusing on spectroscopic follow-up, using Webb's near-infrared spectrograph to measure the redshifts and chemical compositions of individual objects. Spectroscopy is slower than photometry, but it is what confirms the detections and reveals the details. Every spectrum is a biography of the galaxy it comes from. The emission lines tell you what elements are present. The absorption lines tell you how much dust is blocking the light. The overall shape of the spectrum tells you the age of the stars and the rate at which the galaxy is forming new ones. By the end of 2026, the CERS team expects to have spectroscopic data for more than 1,000 galaxies at redshifts above 7, building a statistical sample large enough to test models rigorously and distinguish between different scenarios for how the early universe evolved. There are also targeted observations of individual galaxies that have already been flagged as anomalies. CERS 1019, the massive galaxy at redshift 9 with an estimated stellar mass of 9 billion solar masses, is being reobserved with longer exposure times to refine the mass estimate and search for signs of an active supermassive black hole that might be contributing to the brightness. JADES GSZ 14-0, the galaxy at redshift 14.3 with strong oxygen emission lines, is being studied in multiple wavelengths to map the distribution of heavy elements across its structure and determine whether the oxygen is coming from a widespread population of massive stars or from localized hotspots. These are not quick observations. Each one requires hours of telescope time, and Webb is the most oversubscribed telescope in the history of astronomy. For every hour of approved observing time, there are 10 or 20 proposals that did not make the cut. The competition is fierce, and the pressure to deliver results is immense. Beyond Webb, other telescopes are being brought to bear on the problem. The Atacama Large Millimeter Array, a network of radio dishes in the Chilean desert, is being used to search for molecular gas in high redshift galaxies. Molecular gas is the raw material for star formation, and detecting it in galaxies at redshifts above 10 would confirm that these objects have the fuel needed to build their stellar masses. The Very Large Telescope in Chile and the Keck Observatory in Hawaii are both conducting follow-up observations of Webb's candidates, using their own instruments to verify the redshifts and rule out contamination from foreground sources. Ground-based telescopes cannot reach the same depths as Webb, but they can cover larger areas of sky and provide independent checks on the data. The convergence of multiple telescopes on the same targets is a sign of how seriously the field is taking these discoveries. This is not a single team working in isolation. This is a global effort involving hundreds of researchers and dozens of institutions, all focused on the same question: what is going on in the early universe? The next generation of space telescopes is also being planned with these anomalies in mind. The Nancy Grace Roman Space Telescopes, scheduled to launch in 2027, will have a field of view 100 times larger than Webb's, allowing it to survey vast areas of sky and build a complete census of galaxies at all redshifts. Roman will not have Webb's sensitivity in the deepest infrared, but it will be able to identify thousands of high redshift candidates and pass them to Webb for detailed follow-up. The synergy between the two telescopes is intentional, and it will allow astronomers to map the early universe in ways that neither telescope could achieve alone. Further out, there are proposals for even more ambitious missions. The Habitable Exoplanet Observatory, currently in the early planning stages, would be optimized for studying Earth-like planets around nearby stars, but it would also have the capability to observe distant galaxies with higher resolution than Webb. The Large Ultraviolet Optical Infrared Surveyor, another proposed mission, would combine the sensitivity of Webb with the wavelength range of Hubble, covering everything from ultraviolet to mid-infrared in a single instrument. Both missions are decades away, and neither has been formally approved, but the fact that they are being discussed shows how much appetite there is for continuing the exploration of the early universe. The global collaboration that has emerged around Webb's data is something new in astronomy. The telescope's observations are publicly available within a year of being taken, which means anyone with the skills and the computing resources can download the data and analyze it. This open access policy has democratized the field in ways that were not possible with earlier missions. Hubble's data was often held by the teams that proposed the observations for a proprietary period, sometimes as long as a year, before being released to the public. Webb's policy is more aggressive. The data goes public faster, and the result has been an explosion of independent analyses. Small teams at universities that do not have large budgets or access to major observatories can download Webb's images, run their own algorithms, and publish their own findings. Some of the most interesting results from the first 2 years came not from the big flagship programs, but from independent researchers who noticed features in the data that the original teams had missed. This is science functioning the way it is supposed to, with ideas being tested and challenged and refined by a community rather than handed down from a small group of insiders. The shift in how cosmology is being done is as significant as the discoveries themselves. Before Webb, the field was dominated by large collaborations working on decade-long projects. The Sloan Digital Sky Survey, the Dark Energy Survey, the Planck Satellite. These were massive undertakings involving hundreds of people and producing datasets so large that it took years to analyze them fully. Webb is different. The data comes in faster, the turnaround from observation to publication is shorter, and the barrier to entry is lower. The result is a more dynamic, more chaotic, more exciting field. Papers are being posted to preprint servers within weeks of new data being released. Conferences are packed with talks about the latest high redshift galaxies. Social media is filled with astronomers arguing over redshift measurements and mass estimates and whether a particular object is a galaxy or a quasar. The pace is exhausting, but it is also invigorating. The field feels alive in a way it has not in years. That energy is not just coming from the data. It is coming from the realization that the standard model, the lambda cold dark matter framework that has guided the field for half a century, is being stretched to its limits. The model is not collapsing, but it is being forced to evolve. The parameters are being revised, the assumptions are being questioned. New ideas are being proposed, tested, and either absorbed into the framework or discarded. This is how paradigm shifts happen. Not overnight, not through a single dramatic discovery, but through a gradual accumulation of anomalies that eventually tip the balance and force a rethinking of the fundamentals. The early massive galaxies are the anomalies, and the tipping is happening right now. Some researchers are excited about this. The prospect of rewriting the textbooks, of being part of a generation that fundamentally changes how we understand the universe, is a powerful motivator. Others are more cautious. The standard model has worked so well for so long that abandoning it, or even significantly modifying it, feels risky. There is a tension between the desire to explain the new data and the instinct to preserve what has already been established. That tension is healthy. It keeps the field honest. It prevents overinterpretation of noisy data and forces researchers to justify every claim with rigorous evidence. But it also creates friction. Conferences that used to be collegial are now contentious. Papers that challenge the standard model are scrutinized more heavily than papers that support it. The peer review process, always intense, has become even more so. Journals are rejecting papers that make bold claims without ironclad data, and the bar for what counts as ironclad is higher than it has ever been. The controversy over the early massive galaxies is a case study in how science handles uncertainty. When the first results came out in late 2022 and early 2023, the initial reaction was skepticism. Some astronomers argued that the redshifts were wrong, that the galaxies were not as distant as they appeared, and that photometric redshift estimates, which rely on comparing brightness across multiple filters, were being fooled by dust or foreground contamination. Spectroscopic follow-up has ruled out most of those concerns. The redshifts are real, the galaxies are as distant as they appear, but skepticism has not gone away, it has just shifted focus. Now the debate is over mass estimates. How much of the light is coming from stars versus supermassive black holes? How accurate are the stellar population models used to convert brightness into mass? Are the galaxies genuinely as massive as the numbers suggest, or are there systematic errors inflating the estimates? These are legitimate questions, and they are being addressed through painstaking follow-up observations and increasingly sophisticated modeling. But the fact that they are still being asked 3 years after the first detections shows how hard it is to overturn established ideas even when the data is staring you in the face. The human element of this story is worth pausing on because it is easy to lose sight of the people behind the numbers. Cosmology is not done by machines. It is done by humans with careers and reputations and biases and egos. The researchers who built their careers on the lambda cold dark matter model are not thrilled to see it challenged. Some of them have spent decades refining the model, testing it against observations, defending it against critics. The early massive galaxies are not just a scientific problem for them, they are a personal challenge. And while most scientists are intellectually honest enough to follow the data wherever it leads, that does not mean the process is easy or comfortable. There is grief in letting go of ideas you have spent a lifetime developing. There is also excitement in the possibility that you might be part of something even bigger. A new framework that explains not just the modern universe, but the early universe as well. The emotional landscape of the field right now is complicated, and it is part of what makes this moment so interesting. The younger generation of astronomers, the ones who are just starting their careers, have a different perspective. They did not grow up with the lambda cold dark matter model as gospel. They learnt it in school, sure, but they also learned that models change, that science is provisional, that today's orthodoxy is tomorrow's historical footnote. For them, the early massive galaxies are not a threat. They are an opportunity, a chance to make their mark on the field by figuring out what is really going on. A chance to be part of the generation that solved the puzzle. The energy at conferences, the enthusiasm in the talks, is palpable. These are not jaded scientists going through the motions. These are people who believe they are living through a pivotal moment in the history of their field, and they might be right. The broader public is also paying attention in ways that cosmology has not seen since the Hubble Deep Field was released in the mid-1990s. The images from Webb, with their sharpness and their color and their sheer beauty, have captured the imagination of people who do not normally follow astronomy. News outlets around the world have covered the early massive galaxies, often with headlines that border on hyperbole but are not entirely inaccurate. Galaxies that break the universe, scientists baffled by impossible discovery. The universe is older than we thought. These are not clickbait. They are shorthand for something real, a genuine shift in how we understand cosmic history, and the public response has been overwhelming. Social media posts about Webb's discoveries routinely go viral. YouTube videos explaining the anomalies rack up millions of views. The interest is there, not just because the images are pretty, but because the questions being asked are profound. Where did we come from? How did the universe begin? Are the rules we thought we understood actually correct? These are the kinds of questions that transcend the narrow boundaries of academic science and touch something deeper, a fundamental human curiosity about our place in the cosmos. That curiosity is what drives the field forward, even when the answers are uncomfortable. The scientists analyzing Webb's data are not doing it for fame or fortune. They are doing it because they want to know. Because the universe is a puzzle, and solving puzzles is what humans do. The early massive galaxies are pieces of that puzzle that do not fit where they are supposed to, and the instinct, the overwhelming instinct, is to figure out why. Not to force them into place, not to ignore them, but to understand them. To trace the chain of cause and effect back to the beginning and see how it all fits together. That instinct is what makes science work. It is what keeps the field honest. And it is what will eventually lead to a resolution of the current crisis, however long that takes. The timeline for that resolution is unclear. Some optimists think the answer will come within the next few years as more data from Webb and other telescopes fills in the gaps and clarifies the picture. Others are less sure. The problems are deep, and deep problems take time to solve. It took decades to develop the lambda cold dark matter model in the first place, and it might take decades to refine or replace it. The history of cosmology is littered with puzzles that seemed insurmountable at the time, but were eventually explained. The cosmic microwave background was a mystery when it was first detected in the 1960s. The acceleration of the universe's expansion was a shock when it was discovered in the 1990s. Both of those discoveries forced revisions to the models, and both are now understood as central features of the universe. The early massive galaxies might be the next entry in that list, a discovery that seemed impossible at first but eventually becomes part of the standard story, the new normal. What is clear is that the lambda cold dark matter model, in its current form, is not sufficient. It predicts a universe that builds structure slowly, hierarchically, over hundreds of millions of years. The observations are showing a universe that built massive, chemically enriched, organized galaxies in a fraction of that time. The model can be adjusted, sure. Star formation efficiency can be cranked up. Dark matter can be tweaked to clump together faster. Black holes can be invoked to provide seeds for rapid growth. But every adjustment introduces new questions. Why was star formation so much more efficient in the early universe? What made dark matter behave differently? Where did the black hole seeds come from? The answers to those questions require new physics, or at least new applications of known physics in regimes that have not been tested. And testing those ideas requires more data, more observations, more time. The excitement in the field is tempered by that awareness. Nobody expects a quick fix. Nobody thinks the anomalies will be resolved with a single paper or a single breakthrough. This is going to be a long process, and the path forward is uncertain. But that uncertainty is not a weakness. It is a feature. It is what makes science interesting. If we already knew the answers, there would be no point in asking the questions. The fact that we do not know, the fact that the universe is still surprising us, is what keeps the field moving forward. The early massive galaxies are not a crisis in the sense of a failure. They are a crisis in the sense of an opportunity, a moment when the old certainties fall away and new possibilities open up. The future of cosmology in the Webb era is not a single trajectory. It is a branching tree of possibilities, each branch representing a different way the field could evolve, depending on what the next few years of observations reveal. One branch leads to a refined lambda cold dark matter model, one that incorporates higher star formation efficiency and faster dark matter halo growth without abandoning the core framework. Another branch leads to early dark energy, a modification that changes the expansion history of the universe just enough to make the early massive galaxies fit. A third branch leads to new physics, a fundamental change in how we understand gravity or dark matter or the initial conditions of the universe. A fourth branch leads to something nobody has thought of yet, a mechanism that will only become clear once more data comes in and more theorists have time to think about it. Which branch the field follows depends on the data, and the data is still coming in. Webb is observing every day, pointing its mirror at patches of sky chosen by astronomers from around the world, collecting photons that left distant galaxies billions of years ago. Each new observation is a test. Each new spectrum is a constraint. Each new galaxy adds another data point to the growing catalogue of the early universe. The picture is still incomplete, but it is getting sharper. The edges are coming into focus, and with every new observation, the field is one step closer to understanding what really happened in the first few 100 million years after the Big Bang. The paradigm shift, if that is what this is not happening in a vacuum. It is happening in a field that is more collaborative, more transparent, and more connected than it has ever been. Researchers share data in real time. Preprints are posted online before papers are even submitted for peer review. Conferences are streamed live so that scientists who cannot attend in person can still participate. Social media has become a platform for debate and discussion, with astronomers arguing over interpretations of the data in public rather than behind closed doors. This openness has its downsides. It can lead to premature conclusions, to hype that outpaces the evidence, to public disputes that might be better handled privately, but it also has upsides. It makes the process visible. It shows the world how science actually works, not as a collection of certainties handed down from on high, but as a messy, contentious, collaborative process of figuring things out. The early massive galaxies are not just a scientific story, they are a human story, a story about curiosity and uncertainty and the struggle to understand something bigger than ourselves. The long-term impact of Webb's discoveries will not be limited to cosmology. The questions being raised touch on fundamental issues in physics, questions about the nature of time, the behavior of matter in extreme conditions, the origins of complexity. If the early universe was more active than we thought, if structure formed faster and more efficiently, that has implications for how we think about self-organization, about how order emerges from chaos. Those are not just cosmological questions, they are questions that resonate across physics, chemistry, biology, even philosophy. The universe is a laboratory, and the early massive galaxies are an experiment that nature ran billions of years ago. We are just now getting the results. The human desire to understand our cosmic origins is as old as humanity itself. Every culture in history has told stories about how the world began, where the stars came from, what lies beyond the horizon of the visible. Those stories were not idle speculation. They were attempts to make sense of existence, to place ourselves in a larger context, to answer the question of why we are here. Modern cosmology is the latest chapter in that long tradition, and the tools have changed, but the motivation has not. We want to know where we came from. We want to know what came before us. We want to know if the universe had a beginning, and what, if anything, came before that. The early massive galaxies are not just data points in a scientific paper. They are clues in the oldest mystery there is. And every clue brings us closer to an answer. Webb has rekindled that quest in ways that Hubble, for all its achievements, never quite did. Hubble showed us the universe as it is, vast and beautiful and full of galaxies. Webb is showing us the universe as it was, raw and strange and full of surprises. The galaxies at the edge of the observable universe are not just distant objects. They are messages from the past, snapshots of a moment when the rules were still being written, when the universe was figuring out how to build stars and galaxies and eventually planets and life. Reading those messages is hard. The signals are faint, the noise is loud, and the interpretation is fraught with uncertainty. But the effort is worth it because the answers, when they come, will change how we see ourselves and our place in the cosmos. This is not an ending, it is a beginning. The discovery of the early massive galaxies is not the final word on the early universe. It is the opening line of a new chapter, a chapter that will take years, maybe decades to write. The observations will continue, the models will be refined, the debates will rage, and slowly, piece by piece, the picture will come together. The universe will reveal its secrets, not all at once, but gradually, patiently, the way it always has. And we will be there, watching, measuring, trying to understand, because that is what we do. That is what makes us human. We look at the stars and we ask why, and sometimes, if we are lucky, the stars answer back. The dawn of a new era in cosmology is not a metaphor. It is a description of what is happening right now in labs and observatories around the world, as researchers grapple with data that does not fit the old models and search for new ones that do. The James Webb Space Telescope has given us the tools to see further and more clearly than ever before, and what we are seeing is challenging everything we thought we knew about the universe's beginning. The early massive galaxies are there, glowing in the infrared, impossible and real, and the field, messy and contentious and brilliant, is rising to meet the challenge. The future is uncertain, the path is unclear, but the journey has begun, and there is no turning back. The universe is speaking, and we are listening. So here we are, standing at the edge of what we thought we understood, staring at galaxies that glow too brightly, too early, in a universe that was supposed to take its time. 13 billion light-years away, 300 million years after everything began, structures that should not exist are sitting there quietly, refusing to apologize for breaking the rules we wrote for them. The James Webb Space Telescope did not find what we expected. It found what was actually there, and what was actually there does not fit. The lambda cold dark matter model, the framework that has carried cosmology for half a century, is not collapsing, but it is bending. The observations are too consistent to ignore, too widespread to dismiss, too strange to explain with minor tweaks to the parameters. Something about the early universe was different. Faster, more efficient, more violent. We do not know what yet. We do not know if the answer is star formation running at impossible speeds, or black holes seeding galaxies earlier than physics allows, or dark matter behaving in ways we have not accounted for, or something else entirely, some mechanism that has no name because no one has thought of it yet. What we do know is this: the universe is not obligated to make sense to us. It does not care about our models or our timelines or our textbooks. It simply is. And every time we build a telescope powerful enough to see further, we find that the universe we thought we understood was smaller and simpler than the one that actually exists. The early massive galaxies are not a failure of science. They are an invitation, a reminder that the cosmos still holds secrets we have not earned yet. Mysteries that will take decades to unravel, questions that will outlive everyone working on them today. The lights came on in the universe faster than we predicted, and we are only beginning to understand why.